I'm going to do some coding. It's related to the dictionaries chapter, chapter 9, and we're going to do some word counting. That's basically right out of the slides but I'm going to just write the code in front of you rather than have you look at it in the book. So what we're going to do is I've got my text editor up here, and let me start by making a new folder. For my chapter 9 exercise, and then I'm going to go and make an untitled file. That was from the previous one, and I'll do what I always do, print hello, and save it. And save it here into exercise 09 and ex09.py. So now I have a folder that's in my py4e folder, and that happens to be in my desktop. py4e is my folder on my desktop, and now I have all of these subfolders: cd, ex08, ls is dir on Windows, ls, oops, I got to go up one, ex09, ls. So I've got that file right there. Now I'm going to want to read some files, and so I'm going to bring some files down. A couple of files, Python for Everybody code 3 intro.txt. So I've got this URL, and I'm going to save it, save page as, and it's really important that I save it in the same folder as I'm going to write my code, just so that when I open this file it knows where it's at. So I've saved that one, and I'm going to also take this clown text. I'll use this to make my life simple, so I have a real short thing that I can show you how it works. And so now if I go back to my terminal, I see I've got exercise 09 Python, intro.txt, and clown.txt. Okay? So let's go back to my text editor and get started. I will prompt for the file name, input, enter file, :space. Now I'm going to do something. If the length of the f name that I just read is less than 1, I'm going to say f name equals clown txt. I do this so that I can just hit enter and it defaults to clown.txt. If I want to give it a different name, I can. So if I just hit enter at this prompt, then this will give me a string that's 0 length. So if it's less than 1, I'll just assume that. So let me open that. Handle equals open fname. And let's read through it. For line in handle, we'll strip it. Line equals line.rstrip to take the white space off the right hand side, and then we're going to say print line. Again, I'm not just doing this. When I write code, I just saved it. When I write code, I do these kind of stuff all the time just for my own sanity checking. And so now I'm going to run Python 3 ex09.py just to test that. I'm going to hit enter now, and it's going to assume hopefully clown.txt if it all goes well, and yep, it read one line. Okay, so that part's working. I'll just leave that print statement in. The next thing I want to do is kind of a classic thing where we're going to go read a bunch of lines and then go horizontally across those lines in words. So I'm going to split that. WDS equals line dot split and print WDS. So I'll print that, and I'm going to save it and test it. I really love to test things over and over. There's the actual line. This file, clown.txt, only has one line, and it breaks it into words, and so I have those words. Let's just run it again with intro.txt. So this will have a lot of lines, line, lots of lines. Every line prints out the line and then prints out the words that we split it into. Okay, so now one of the things that I do here is I want to believe, now I sort of can believe everything from here up. Like, oh, it's going to open the file, it's going to read through the lines and going to split them into words. And so then I'll just kind of behind it, I'll just say, okay, I'll just I'll just comment that out. Now I need another for loop for W in WDS. Now words is a Python list and has some number of words in it, 0 or 12 or whatever was on the line. And now I'm going to print out the word. Okay, and so now it will go through that horizontally. Now I'll just do clown.txt so that you see I'm not printing the line out. That's the words that have been parsed split from the line. And now we got this loop. Now, one of the things that's interesting is just to make sure that you're going through all the words. And I like a print statement here to know that W is going to successively take on literally all the words of this file. So if I comment this print statement out and I run it again, clown.txt, that for loop starting from here is every word in that file, which happens to only be one line. But now if I do the same thing for intro.txt, it's just going to go through the words. And in a sense, by nesting these two loops, we're going to hit all the lines. And that's a lot of stuff, but it hit all of the lines, all the words, and away we go. Okay, so here's where a dictionary comes in. I'm going to make a variable called di for dictionary, and I'm going to say give me a dictionary. Now dict is not something you can choose. That's saying that's defining the type of dictionary. Di is a variable that I chose. Okay, so the key thing to this dictionary is we're going to make a counter, and we're going to use W, the word, absorb, elegant, whatever, and we're going to use that as the index. So the simple thing to do is to say if W is in di, then we can say the dictionary sub the word, which is our key in the key value store of the dictionary, is equal to the value that we had before in that area, d sub W plus 1. And if it's not in there, else di sub W equals 1. And I'm going to print print new. So every time we see a new word, it's going to say new. And I'm going to also then print W and the current value of the counter for W as it's going through. Now notice how far in I'm indented. This is all part of this inner loop. So this is the loop that's going to run every single word. Okay? And I'm going to run this first with clown, so it runs slowly. Okay, so we saw the was new, and the count is 1. Clown is new, count is 1. Ran is new, the count is 1. After is new, the count is 1. Now we saw the again, but now we made the count be 2. Let's print here. I'll say existing, so you can kind of see it. Now in the print, I'm printing this. Let's make it even a little more verbose. Print W, and then I will make it so it prints the word before and the count after, and then whether it's existing or new. So we'll put a lot of print statements in. Print statements are cheap. Okay, so now we see the word the. It's the first time we see it, and we set it to 1. We see the clown. It's the first time we see it, we set it to 1. We see ran, new, 1. Later on, we see the. It's already in. So existing means it was already in the dictionary. W as a key was already in the dictionary. Okay, and so that's why we added 1 to it. So the old value was 1, and then we added di sub the equals di sub the equals di sub the plus 1. W is the string the, the. That's what that string is. Okay, and so we've made it all the way through, and you see the in this one line occurred ultimately 7 times. So now I want to print out the contents of this dictionary at the very end of both loops. So I got to de-indent twice. And so that will give us the counts. And so this is what we get when it's all said and done. You know, the happened 7 times, but it just worked through its way through. Okay? So you got that. Now, this is a pretty verbose way of doing this, but I did it sort of the slow way to show that there are 2 situations. If it's already there, you increment it, and if it's not there, you set it to 1, effectively inserting it, right? So you insert it and set it to 1 with this di sub the equals 1. Okay? But let's get a little less verbose here, get rid of some of these print statements because we kind of covered all that. Get rid of this line and go back to printing W and DIW at the end. We'll leave that one in. So what I want to do is I want to look at this bit of code right here, this if W in DI else. We do this so much with dictionaries that there is an easy mechanism to do this that combines these 4 lines into a single kind of contraction. And so I'm going to do this. I'm going to print, let's put 2 stars out, then the word and di.get of the word, comma, negative 99. Okay, and so this di.get of the word is the important part. The way it is this is a dictionary. .get says in its first parameter is the key to look up, which is word like the or fell or clown or whatever, and 99 is the default value that we get if the key doesn't exist. So this is in effect an if then else, right? This little di.get w99 negative 99 is, you know, if it's in there, do one thing. If it's not in there, do something else. Okay, so let me show you how this works, and you'll see that the 99 will happen when okay. So the first time we see the, get returns 99. Right? So let's move it over here. The first time we see the is not in the dictionary. So this di.get of the word the in the dictionary gives us back the negative 99. Okay? And this still is working, and so the is 1, clown is whatever, but away we go. Okay? Let's do it this way. Let me comment this out. Let me comment this one out and run it again so it's a little clearer what's going on. Okay. So the first time we see the is not in the dictionary. The first time we see clown, and we know it's negative 99. But here we asked for it, and the is 1 because we'd seen it before. And so that's just this get mechanism allows us to get the new value, or get a value out if the key exists and specify a default if it's not there. So I'm going to go old count equals di.get w, comma 90, comma 0. So instead of using 99 here, I'm going to just get rid of all this. Is what I'm saying is look up in this dictionary. Get is a function that's part of all dictionaries. Look up using the key w, which is the, and if I don't get it, give me back 0. And so I'm going to say print word, comma, old, comma, old count. And now what I can say, whatever the old count is, it's either the value that was in there or 0. And now I can say new count equals old count and now, let's see, new count, and I can say dictionary sub word is equal to new count. So instead, I'm going to get rid of this if then else then. This is basically saying look up the old count that we have. If you don't find one, use a 0. We'll print that out. And then I'm going to say afterwards I'll print the new count. Now, and so we'll print the old count. Here are some of these blanks. Print the old count. And you can see the old count with the, because the doesn't exist, was 0. The new one's 1. Clown's old is 0. New is 1. Clown's old ran, old 0. But now we get to the, its old count was 1, and now its new count is 2. Okay? So by using this get and saying if we don't find it, we'll assume the count is 0. That makes a lot of sense, right? You know, if not there, the count is 0. If the key is not there, the count is 0. Okay? So that's what this line does. If get the value from under the key be associated with the key, or give me 0 back. And then I can take that old number and just add 1 to it and then stick it back in. Now this is ultimately not how we tend to do it. Okay? We tend to blend this all into one big long statement. di sub w equals this part plus 1. Okay, so that says get the old value from this key or 0 and then add 1 to it, because that really combines all of these lines into a single line. Okay, so I'm going to delete them now. And now we've combined this all into one, what effectively is an idiom. Retrieve, create, update, counter, all in one line. I'll still print out, in this case I'll just say di sub w, and then we'll see the counter. Okay, and so now I'll run this. We have a new, but now we see it the second time it's 2, and so we see car the first time, we see that the second time, we see car, the third time, we see car the second time, and away we go. Okay, and so that's pretty straightforward, and so it really kind of a typo there. So let's just get rid of that and run it with the clown stuff, and we get the right data there. And let's run it with intro.txt. And there we go. Okay? And so it's tearing out a bunch of words and giving us a dictionary. So that was a lot of work to get to this line 16 that has the dictionary in it. Now we want to find the most common word. And so we're going to loop through this dictionary, and part of it is like, once we printed this dictionary out and we verified that it's right, don't worry too much about the code up here, right? Matter of fact, I can take out some of these print statements, and we can kind of trust all this. And so now we're going to work on this. Okay, now we want to find the most common word. Now this is like a maximum loop. So if you recall, we have a whole set of key value pairs. Communicate goes to 2, is to 2. Skills is 3. So we have these key value pairs, and we're going to loop through and look for the maximum. Now, in a dictionary, we can loop through the key value pairs with the following syntax. For, I would call these variables k and v for key and value, but in the dictionary's name dot items. And items is a method inside of all dictionaries that says give me the key value pairs, and we need 2 iteration variables. So this is like an assignment statement for k and v. K and v take on the successive values for the keys, the key and the value. Okay? So if I just now print k comma v, and I'll take this print statement out and then run the code, on, oops, what I forgot to, oh, I fell back into my Python 2 days. Need parentheses for my print. So there's clown, and it just prints it out. And it's kind of the same thing, except it's pretty, where we're putting each one on a line. Okay, so the V is the value. So we're looking for the largest value. Oops. So the thing is, we know that the values are always numbers that are greater than 1. So I'm gonna do kind of a quickie maximum loop. Largest equals -1. Now in previous times we've seen that this is a bad assumption, but because we know these are counters that are always positive, it turns out this is not a bad idea. And so I can say if the value is greater than the largest we've seen so far, largest equals the value. Okay, and when that loop is all done, we can print the largest. Okay, and so this is just a max loop, and we're using this value. That's the number. The value is the second thing. Oops. Can't type Python. Oh, it's a typo. Yeah, I'm not using value, I'm using V. So largest equals V. Let's try it again. Okay, so we're all done with 7. So these were the things that we were looking for, and it was looking for the maximum, and it just dutifully found 7 was the largest. But we also want to know what the word is. And so what we can say here is we can say the word is none, meaning it's just like we don't know what the word is. And then whenever we catch this new largest number, we say the word equals W. So I like to think of this as capture, remember the word that was largest. Right? That's what I'm doing. Remem remember. Right? That's R-E-M-E-M-B-E-R. There we go. So we're gonna this trick here is not only knowing what the largest number was, but the word that was associated with the largest number. So now I can print out at the end the word and the largest, and that's the count. Okay, and so now we know that. Oops, did we make a mistake here? Okay, that does not look good because it says car and 7. If V is greater than the largest, oh, it's not W. I used a really bad variable. See, that's the old value there. There we go. It's K, which is the key. Key. I was going to say that was quite the bug. See what happened there? I had this as W, and it just happened to be it was the last word on the file. Car, the last word in the file, because I used a wrong variable. Right? No, little mistakes, little mistakes. The and 7. Okay, so let's get rid of this print statement because we kind of know what's going on here. And away we go, and this should now work if we run it. We can even get rid of the word done here. There we go, the 7. Now, the cool thing about this is this code runs just as easily with one line of code or the intro of the book, intro.txt, and not surprisingly, that's still the most common word in the introduction.txt. I seem to like that word, and it's 226 times. Okay, and so that is the basic pattern of reading some. This is just a word loop. Now sometimes there would be some, checking to see if the line is the one you're interested in, maybe tearing apart the line, but it's at the end of the day, this idiom of starting a dictionary. Now it's a common problem to know where to start the dictionary. You want to accumulate the numbers for the whole file, so you don't want to put it in between line 6 and line 7. Okay? So I hope that particular thing helps a little bit, helps you understand dictionaries. Hello and welcome to Chapter 10. Now we're going to talk about our third kind of collection called tuples. But tuples are really a lot like lists. There's not too much to them. They're really kind of reductionist version of lists. So they function very much like lists in that they have things, and the difference is there are no square braces. There is a parenthesis, round brace or whatever, and they have positions 0, 1, and 2, just like a list, and you can look things up, x sub 2. So x sub 2 is actually the third element here, and so that prints out Joseph. You can assign, make a tuple here. This is the constant syntax for a tuple, and print that out, and the print statement shows you that this is a tuple, not a list, by showing you round parentheses, and a whole bunch of functions that work with lists work the same way with tuples. You can put a tuple at the end of an in statement in a for, as you might expect, and then it iterates through the tuples. Tuples maintain order, so it prints out 1, 9, and 2. So literally this bit of code here could be identical whether it was a list or a tuple. It really would do the exact same thing. The difference between tuples are that they are immutable. Once you create the tuple, you can only sort of assign a tuple, but you can't modify it. You can modify a list. So if we take a look at a list here, we make a list that's 987, and we say x sub 2 equals 6, well, that just means this 7 becomes a 6, and that's just natural, meaning we can reassign slots. We can delete things, we can insert things, we can mutate them, we can change them, so they're changeable. Right? They're changeable. But if we try to do that same thing with a string, so we say y equals ABC, and we know that this is position 0, 1, and 2, but if we try to say, let's change the C to a D by saying y sub 2 equals D, that is not allowed. And it says it doesn't support item assignment, and this little bracket, x sub 2, is what they call item assignment inside of Python. And so if we do the same thing then with a 3-element tuple, put that in Z, and we try to change this slot to be a 0, it's going to blow up because it's the exact same thing. And that has to do with the fact that once this assignment is made, this is not modifiable. Now, it turns out that the reason it's not modifiable is for efficiency. They take up less storage, they are quicker to access, and they're really designed internally behind the scenes in ways we don't really need to understand. They're just more efficient than lists. If all you want to do is store a list and look at it and then throw it away, you probably should use a tuple instead. So there's a lot of things that you can do with lists that you also can't do with tuples, but they're really just a corollary of this notion of non-mutability. And so, like, you can sort a list, but you can't sort tuples. You can add a 5 to the end of 3, 2, 1. Can't do that in a tuple, but you can in a list. And flip the order. ... So anything that you can do to a list that modifies the list, not allowed for tuples. And so you can take a look at the kinds of things that are inside, the methods that are part of each list: append, count, extend, index, insert, pop. Many of these are modifying, and then count and index are the only ones that work for tuples. And so tuples are limited lists. Now, at some point, there's going to be a but here to say, why do we like them? And the reason that we like them is that they're just more efficient. They don't have to build Python in its own internal organization of these objects. It knows that they'll never be modified, because when you make a tuple, you as the programmer are saying, I'm never going to modify this, and Python won't let you do it. So it's higher performance, better memory use, and to a beginning programmer that doesn't really matter, but that's the reason. And so we tend to use tuples when in situations where we're going to make a temporary variable and then temporarily use it just a little bit and then throw it away without really messing with it. And we tend to use lists to build things up, etc., etc., etc. So the other thing that's interesting about tuples, and we've actually sort of seen this, is that you can put a tuple that includes variables on the left side of the assignment. And This takes a little getting used to, but it's really cool, and no other language that I know of does this. So if we say x comma y, that's a two-tuple. Both have to be variables. You can't put constants on this side. You know, it's like saying x equals 4, y equals Fred, right? So what happens is you can put a tuple on the far side of an assignment statement, and the 4 goes to x, and the Fred goes to y. And you say, what's in y? Well, y is indeed Fred. And so this is like two assignment statements. Now, the way I've got this syntax, I would probably do, you know, two separate statements, just not to show off that I know how to do tuples. You know, and so you can, here's another one, and they just move correspondingly. If you don't have 2 here, and you do have 2 here, well, if you have 3 here, or 2 here and 3 here, and you don't match the number there, you get in some trouble. Now, if you just say x equals tuple, then that is the tuple in the list. But this is just a simple straight 99 value going into A. So you can put tuples as the left-hand side, and you can even do things like return a tuple from functions. That's a real nice Python feature that I like a lot. Tuples are also related to dictionaries, as we've seen in the previous chapter. So here we make a little dictionary. We make an empty dictionary by constructing an empty dictionary, stick it in D. So D is sort of like this place that can hold key value pairs. And we put csev, and there's a 2 in there, and chen1, and there's a 4 in there. So we have this, you know, associative mapping between csev and 2 and chen1 and 4, all stuff we know. And now we say, hey, we're going to loop through the key value pairs here, and we've seen this syntax before, k comma v. So this is a tuple. So you can think of this as each one of these things is going to get assigned into this tuple, which means the key ends up in, and the first one's the key and the second one's the value. I use the variable key kv all the time in code that I write, just for my own sanity. So kv are going to iterate successively through the successive keys and values in that. So this is going to run twice, and k is going to be csev 2 and chen1 4. The order just happened to stay the same. And so if you say what is in one of these things, you can actually take d items, the items method within that dictionary, and say, hey, give me back, give that to me back, and then print tups. And this is, it's a special kind of a class, but really ultimately it is a list of tuples. You know, this is 2. This is the 0, and this is the 2, the 1, the first and the second. And then within each thing you get, you have a 2-tuple. And so, in a sense, this k and v are iterating through those things when we're putting d items here and d items there. One nice thing about tuples is that they're comparable. They're comparable in the same way that strings are comparable, meaning that they're compared from left to right, with the leftmost or 0 tuple being the most significant. And it doesn't compare any further than it has to if it's asking less than. So if it's looking at, say, this first tuple, it starts at the left and says, okay, ask the question, tell me true or false. Is 0 less than 5? The answer is true. And so the answer to this overall expression is true, and it doesn't even compare those two numbers, those second and third number. They don't compare them. If, on the other hand, we're asking is this less than that, it only looks at the first one and asks if it can answer the question. And the answer is, well, they're both 0. And so I can't answer the question, so I have to go to the second one, second pair, and 1 is less than 3, and so that means this is true. And it does not check this. Even though 20 million is bigger than 4, it doesn't matter, because these are the numbers that cause the true to happen. And the same is true if you do this with strings. Again, we start the first one. So Jones, Sally, well, that's the same, so we don't know the answer yet. And so Sally, Sam, well, okay, S, oh, they're the same. A, they're the same. O, L, and M. L is less than M, so the actual letter that makes the difference here is the L and the M, and leads to us being true. And so it goes left to right, but then even when it's doing strings, it's going left to right. That's just how string comparison works. And if we say is Jones Sally greater than Adam Sam, well, we check the first one and we check the J and the A. Well, J is greater than A, and so we don't have to look at anything else. We don't have to look at any more of these characters. We don't have to look at the second thing in the tuple. We have to look at that is enough to be true. So it only scans until it has a definitive answer. It doesn't scan any further. So now what we're going to do is use this comparable capability to sort these lists of tuples and then bring this all back and connect it more to dictionaries. So now we can take advantage of the notion of comparing tuples and use sorting. And so what we're going to produce is a list of tuples, and then we're going to sort them, right? And so we can get a list of tuples from a dictionary, and then we can sort that list of tuples, and then we can end up sorting dictionary items by taking this two-step process. Convert dictionary to a list, sort the list, and then we can have assorted dictionary values, okay? And so we'll do this a couple of different times. So if we take a look at this code right here, we have our happy little dictionary, A, B, C, A maps to 10, B maps to 1, C maps to 20. Like, what are we going to get here? Well, it comes out, the mapping is the right way, but the order is whatever. And now we say this function called sorted, which takes inside a sequence and then returns us a sorted version of that, a list that's sorted. And so it says sort D items. So it's basically going to take this list and compare the A's and the C's and the B's, and because it's a dictionary and all the keys are unique, there's never going to be equality, so it really is going to just sort this by keys and never get to looking at the values. You could construct a list that had duplicate, you could make a list of tuples that had duplicates in the first, like we did before, but given that this coming from a dictionary, the first thing is going to always be unique and distinct. And so if we say sorted D of items, that we're passing this stuff into sorted. Sorted is going to go around, move stuff around, and then give us back a sorted version, sorted in ascending order based on key, without looking at the value. And so that's a way to see dictionaries sorted by key, is just say sorted of D sub items, and sorted is a function, and so it just picks stuff. And so this is the kind of loop that you're going to write to do that. You know, we did this before. We took sorted and we got these sorted by keys. And so you can just make this nice and simple for key value. By the way, you can eliminate the parentheses here, and I think it's prettier if you eliminate the parentheses, but you could put parentheses. This is still a tuple without the parentheses for key and value in sorted. So that says go through D items, but before I go through them, please sort them. So that means K is going to go through A, B, and C deterministically every single time it's going to go. And of course, value is going to go through the corresponding values. So now we can print this out nicely, sorted by key. And that's a real nice, succinct little way to say that. I mean, again, these are one of the kind of things that people really like about Python, is that you can do pretty powerful things with easy to understand. I mean, you might have seen this for the first time, but ultimately you look at that eventually and you'll be like, oh yeah, I see exactly what that's doing. Easy, not hard at all. So, but let's say we're looking for the most common word, which we have been for weeks and weeks and weeks now. And so we want to sort by values, not key. So this is an example of where we're going to construct a data structure. We're going to imagine a data structure, and then we're going to write code to construct the data structure, and then that's going to make our problem easy. So this is an example of using cleverly constructed data structures to do this. And the data structure that we're going to create is a list of tuples where the value is first and the key is second. So you can just with items get key value. I want value key. So let's take a look at this code. Take your time and get it right. So KV goes in C items. Well, that is unsorted and going to go through whatever A, B, and C in whatever order. And we're going to make a new list. So this is a data structure that we're creating temporarily. And what we're going to do is, this is a list, and we are going to append to that list a tuple. So this is going to be a list of tuples. Except we're not going to append them in key value order. We're going to flip them and append the first part of the tuple is going to be the value and the second part is going to be the key. So we end up with this. This is sort of our temporary data structure that we have constructed to make our job really easy. So this ends up being 10A, 22C, 1B. Now we just kind of flipped them. We took this order and then we flipped them around. And so now we have this nice little list sitting in memory in a variable. And that's really simple. We can say, oh, look, we can use sorted. And we can sort by now the values because they're the first thing. I mean, the sorted doesn't know that they're how we produce this list. It just looks at that and says, oh, that's a list of tuples. I'm going to always sort by looking at the first item in any tuple. And I'm going to add reverse equals true, so I get a descending sort. So I see that the value that is highest ends up being first. And so that changes this, and I'm just sort it and then reassign it back into temp. And I'll print this out, and so now you see it sorted in descending order of key. So it's value, key, value, key, value, key, but it's sorted in descending order. Okay? And so that's an example sort of just like, you know, if I just made a data structure and I flip those things around, I could use sorted to sort these things. There's many other ways you could do it, but there's sort of like the more elegant way of doing it. And the clever bit here is like make a new list and make it be a little bit different. Okay? So here we're going to print out the top 10 most common words in a file. And most of this code is review, so if we take a look at it, we're going to open a file. We're going to start a dictionary for our counting. We're going to, you know, there's going to be words and lines, right? And so we're going to have a for loop. This for loop is going to go through each line. And then, of course, we're going to split them, which is busting them into pieces. And then we have a for loop within that, and this for loop is going to go through each word. And so that means that by nesting these loops, we're going through each line, and then within the line we're going through a word. Then we go to the next line and go through the words. And eventually this line of code, count subword equals counts.get word 0 plus 1, our idiom for making a histogram, right? This line right here is an idiom. If you don't know already what that is, go back to the previous dictionary lecture and understand it, because you're just going to use it over and over again. So now at this point, and I always like drawing horizontal lines in code when we write it, at this point, coming through at this point, counts is right. Counts is the histogram. It's not sorted. So now we want to sort it. So we're going to make a new list. We're going to loop through key value, and then we're going to make a tuple. I'm making this be 2 lines to make it a little easier. Value key, so I'm flipping it, right? So I'm flipping the order of these things. That's making a tuple, and then I'm appending that tuple to the list. Okay? So at the end of this, we have a list of tuples in value key order, VK, VK, right? So at this point, coming through here, I've got in my LST variable, I've got this really useful bit of code, or useful bit of data that I produced. And then I'm like, oh, now it's ready to be sorted. Poof, sort. So take list, sort it back, and sort it in descending order, and then stick that back in list. Now, we want to print it out, but we don't want to print it out. So we got a nice sorted list coming down here. We don't want to print it out in value key, because that's what it is. It's in parentheses v comma k order, but it's sorted. And we know that the highest value is here on down. And so we're going to say, you know, we're going to run through, and now we're going to go through this new list, only the first 10, start at the beginning up to, but not including number 10, which is the first 10. For value key in, and so value is good. So this is the iteration variable that's going to go through each of these things on and down, and then we're just going to print it out flipping it. So we re-flip it, flip, flip. We print it out key value, and it's going to work. Okay, so that is one way of doing this, and this slide right here you absolutely do not need to figure out. But some of you will look at this slide and you're like, why didn't you show us that in the beginning? And others of you will be like, no, 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 no. Keep telling me this stuff here. So I don't know exactly the term for this, but this is a very procedural. This is a classic algorithms and data structures approach to solving this problem. This next thing uses what are called lambdas, and they kind of create what's called what I call a closed form, where you kind of do it in all one statement, and there's all this implicit stuff going on. So if you don't get this right away, don't worry too much about that. But roughly, this single line does everything that bottom half of that program does. I mean, if we go back to here, it's pretty much this line does everything, does that in one line. Okay, it doesn't create the counts and it doesn't print out the top 10, but it does everything in that middle bit. So let's take a look at this. So we all are going to collapse this down. So we have a print, that parentheses the end of the print. And then we have sorted, and remember that sorted takes as input a list. And so that's not too bad, and returns us a list. And so we'll print the return from sorted. And then this is the funny part, the fun part, funny part. This is called list comprehension. And we have square brackets and we say to Python, this is a list. But instead of listing the things or having a constant of 1, 2, 3 or append, 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 we are going to create an expression that will act as a generator for all the elements. And so this basically says, this is a list of two tuples, v and k, and then this is sort of implied. For all kv in c.items. And so this is like a for loop that is sort of driving this. Think of this as like stamp, 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 stamp. However many times it has to make a stamp. And so that's producing a list, right? It just manufactures this list. And then that list is sort of manufactured in the moment. There's no stock, it's not put in a variable. Python makes that list according to the stamping pattern that you've told it to stamp out this list, and then it passes that stamped out list without even storing it in a variable into sorted. Sorted moves the list around because it is just a list of tuples, and then gives us back the sorted list. And so I didn't put reverse equals true on here, but you see that this is sorted in ascending order now by key. And I did that all in one little statement. So look at this. This is also one of the beautiful things about Python, that you can build these things and you can build more complex versions of this, and there's a lot of real elegant things that you can do in Python. They're really succinct. You should be careful because in the beginning I think this is easier to understand, even though after a while you're like, wait a sec, why am I putting all these extra lines in? Because this is not so hard to understand, but at some point, you will want to master this more powerful and more succinct version of Python that expresses it in terms of what the data you want to see rather than the steps you want to take. So this sort of finishes up tuples. We've done a bunch of stuff. I mean, really, they're simple and elegant. Tuples, lists, and dictionaries are all related. They're really three different, three foundational data structures, three foundational collections of Python. And we combine those in a lot of different ways. And now in this little bit of lesson, we're going to talk about some tuples. And we're going to create a list of the most common words and find out how to sort a dictionary by the values instead of by the key. We're going to use the clown.txt file and the intro.txt file. And I'm going to start with the code from exercise 9 that I just did from chapter 9. It's not exactly one of the exercises, but it's very similar to them. And I'm going to make a copy, and I'm going to keep it in the same folder. I'm going to keep it in the EX09 folder and just call it EX10, because this code is going to do much of the same stuff, and it's going to read these same files. And so I've got myself exercise 10. Exercise 9 is still here. Exercise 10 is now what I'm editing, exercise 10. But I'm in the exercise 9 folder. So in exercise 9, we look for the most common word, but we want to find the 5 most common words, which is going to require us to sort. So I'm going to get rid of that code because it's not really how we're going to do it. There we manually looped through it and found the maximum. And so I'm going to just run this. cd desktop python for everybody ex09, and if I do an ls, you see that I've got ex09.py intro.txt. So I'll run python 3 ex10.py and run the clown data, and we see the dictionary, and it's properly making it in this code right here. That doesn't change. It reads the file, reads all the lines, goes through and splits it into words, and then goes through the words and does the idiom of using dictionary get to maintain the counters, and we print it out at the very end. So the new code we're going to write is down here. Okay? So let's first do a few things. If I can say x is equal to the dictionary dot items, and this gives us basically a list, print x. This gives us a list of the key value pairs. This prints out the dictionary, but if we do it this way and use items, it gives us the key value pairs. Okay, and so that's what we got. Key value pairs. Now, we can sort this based on the value, because tuples can be compared. This can be compared with this, and because D is lower than R, then this one is lower. This whole this ran tuple comes after the down tuple. So we can sort this whole thing. And I'll do this by just putting the word sorted here and say, give me a sorted version of that. Now it's going to do it based on the order of the tuples. This is going to be higher precedence than this. So if I print it this way, run it again, you'll see that it's sorted. And now is after and car, it's in alphabetical order by key. And so we could actually print the first 5 up to but not including 5 by adding a list on the slice, a list slice here. And so that will show you only the first 5, right? Except that that's not what we're trying to do. We really want to sort by this. Okay? So we have this mechanism that can take a list and sort it based on the tuple values. If we could create a list where it was 1 comma after instead of after comma 1 and make it the exact same thing, then we could actually then sort it and it would be fine. Okay? So let me show you a couple of ways, at least one way to do that. Okay? Get rid of this. We're going to hand construct a list. And just call it temp equals, give me a new list, temp equals new list, and then for k comma v in the dictionary.items, and I'll just start by printing k comma v, so we see, and this is where it's really nice to do these with the clown code first and then only do your test on the bigger file later. And so it's pretty much the same thing. We are going through in key value order, which is dictionary order, which is not sorted at all. Okay. Now, instead of printing this out, we are going to, let me do this in a couple of steps. Make a new tuple, and we'll just call it newt equals parenthesis v comma k. Okay, so this is, I'm saying make a new tuple. This is like a new tuple with 2 items in it, and I'm going to make the value for and the key. Okay, so then I'm going to say temp.append newt, new tuple. So I'm going to end up with a list of tuples. Let me comment this one out, and I'm going to then, when I'm done here, I'm going to print temp. So if I run clown.txt, you see what happens in temp. It's still, well, let's print temp twice. I mean, it's not sorted, it's flipped. Let's print it. Well, that's okay. That's the flipped one. Okay, so it's flipped, and all we did is we made it, instead of car comma 3, it's 3 comma car. But now we have a list. Okay? So now it's flipped, and now we can sort that. We can say temp equals sorted temp. So it says takes temp and sort it and give it back to me. And now I'm going to say print sorted comma temp. Okay, so here's the first print. When we flipped it, we've got 210, but it's not sorted at all. But after we sorted it, it's sorted by tuple, and the lowest is 1 after, so you'll notice that 1 is the same as 1, so it checked the second item in the tuple, so down comes before after. Fell becomes after down. Intro, on, alphabetical order, but now we get the 2's, so that all the 1's sort there, and then the 2's come here, but then within the 2's it's sorted in alphabetical order, because like a string, if the first character matches, then it looks to the second character, and then we see, oh, here we go, the 3's, and then the one we actually wanted, the highest one, is the 7. And so one of the things we can do is we can say, you'll notice that we want the highest one, not the lowest one. So we can just tell this with this parameter, reverse equals true. And we just say, hey, sorted, do this backwards. Do it from highest to lowest rather than lowest to highest. And now our sorted one says 7, the, etc. Okay? And so if we want the first 5, we can say up to but not including 5. So this is now the top 5. So the sorted one is, that's the top 5. If it's a tie, we're going to go in reverse alphabetical order, but let's not worry about that too much for now. So it makes a flipped list, then it sorts the flipped list. Now, if I just wanted to print it out nicer, I could loop through this new list. I could say for v comma k. Remember, this is a flipped list, so the sensible thing is what's coming out of this list. Each tuple is value comma key in temp, and I'm only going to go up through but not including 5. So the first 5, and so I'm pulling them back out as value key because that's what they are. They're value key. See, value key, value key, value key. So v is going to go through these, and k is going to go through these, and then I'm just going to print k comma v. So this is kind of my flipping backwards because I want to see them this way. And the is the most common one, car 3. And so it's just going through this up through the 5th one and then printing them out. Okay? So let me comment this out. Let me comment that out. Let me just delete this. So we have a dictionary. Let me comment out the dictionary. We have a dictionary. We make a list, and we make these reversed tuples where we have the value first and the key second. We're setting it up so the sort's going to work. And then once it's sorted, we have to flip them back. So we flip them for sorting from key value to value key for sorting. We do the sort, then we flip them back with key value and print them out. And it works fine. So let's try our big file, intro.txt, and there you go. Those are the 5 most common words in intro.txt. So you might ask yourself, why did we use tuples? We could have really used lists for this, but tuples are more efficient than lists, and you notice that we weren't going to modify. We did modify the temp list. It's a list of tuples, but the tuples within the list we weren't going to modify. And so we tend not to make lists if we can get away with using tuples. And so that's why we made this this flipped tuple thing. Okay, so I hope that was useful to you. Hope to see you on the net.
Hello and welcome to Chapter 11, Regular Expressions. The fun thing about this chapter is, unlike all the rest of the chapters, you sort of had to really understand every single thing in chapters 1 through 11 built on one another, 1 through 10 built on one another. But you can really get along without using Chapter 11. It's not a really required topic, but it's a fun topic and an interesting topic. So you can relax a little bit and realize that you may or may not like regular expressions, and if you don't like them, that's okay. You don't have to use them. You can go for your whole life without using regular expressions. The idea of a regular expression is that you come up with a language. It's a little character-based programming language where you can do smart searching, basically. Smart searching, and as you'll see in a bit, was smart extraction, and it's really almost programmable wildcard expressions. There's no looping, but there is looping, and there's all this implicit thing. And you say, look for patterns that look like this, and then you get back things that match those patterns. You know, we do searching for everything. We're looking through large blocks of text. Say, go find me everything that has the word Python in it or something like that. So that's just such a common thing to do, and regular expressions are a very structured way to go about searching for information. They're very powerful, but they're also very cryptic, and you may not like them, but they're a lot of fun actually once you understand them. Learning how to program them takes a while. Writing good regular expression programs requires some try it, play with it, check it, try it, check it, try it, check it. But once you get them, they're really quite cool. It's a very old programming language. You know, it comes almost from the 1960s. The concept of, it's the theory of computing, where they were trying to come up with theory of languages, and regular expressions was one form of languages that computers could understand. And so it has some fun old words. And one of the advantages of knowing regular expressions is that you're kind of a cool person. You can take a quick look at this XKCD that sort of captures the devil-may-care awesome power that regular expressions do. And while we're at it, you know, while we're talking about awesome, I do want to take this moment and show you my awesome tattoos. And so you may not know this, but I got a couple tattoos here. Here's the first tattoo. This is where I got my PhD, and this is my University of Michigan faculty member position. I got PhD in engineering, and I teach in a school of information and library science. And then I have this other tattoo, and this tattoo is what I call the Ring of Compliance. I work on learning management systems and educational technology and standards, and there's this standard called Learning Tools Interoperability, which if you're using this course and doing the autograder, it uses Learning Tools Interoperability to integrate into whatever learning management system you happen to be using. And one of those learning management systems is the open source learning management system that I helped write called Sakai, and these are the rest of the major vendors. And the idea of that tattoo was that I would put the tattoo of every vendor that would comply with Learning Tools Interoperability. And so you'll notice Coursera. I helped Coursera put Learning Tools Interoperability in, and so the autograders integrate into Coursera or Blackboard or Canvas or Sakai or Moodle or half a dozen other things. So it's just like a cool techno thing, just like regular expressions. So I've got a URL here for regular expression quick guide. You might want to print this out so that you can look at it even while you're watching this lecture, because it's a little programming language, except that it's character-based, not line-based, and not keyword-based. It has certain active characters that the character means something versus the character represents the character itself. And so the regular expressions is not part of the base Python, but it's distributed with Python, so you have to put an import RE at the top to say that's really saying pull in the regular expression library. And there is a couple of functions inside that, re.search, which is kind of like a really smart version of the find method inside of strings, and re.findAll, which is kind of like taking and stamping your way through a loop, through a string, and finding all of the things that match a particular pattern and then extracting those. And we'll talk about both of these in this lecture. So here's a really simple piece of code where I'm just going to sort of show you sort of before and after. So here's a thing where we're looking for lines that begin with from : and so we open a file, we loop through the whole file, we strip off the lines text, and then we say if line.find from is greater than or equal to 0, then we print it. It gives you -1 if it's not found, and so reads all the lines, and once in a while it'll print it out, reads all the lines once in a while, print it out. So that's kind of like a needle in a haystack. To use regular expressions to do that, we have to import the regular expression library. These lines are the same. We're going to loop through. We're going to strip. And now we're going to say if re.search. The way to say this is within the library regular expressions, go find the search function and search for the string from in the string line. Okay, so this is the line to search, whereas here it was more object-oriented where we say line.find. Here we say re.search and we pass in line as parameter. These two things are equivalent, which means most of the time it's going to run, and once in a while it'll hit a line and it'll print that out, and then it'll finish the whole thing. So that is taking and doing what we would do with the find operation with regular expressions. Now, searching with regular expressions has these special characters, and so here we have the same basic code, except now we're saying if line starts with from. So we're not using find anymore. And that way we're only going to get that thing in the first position, not like blah, 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 blah from : We don't want that to match. We only want it to match here at the beginning of the line. And so that's what we use line starts with. So it's going to do the same thing and find lines that have the prefix and print those out and then be done. Now in regular expression search, we don't, in a sense, change the method. We have a certain number of things we can do with strings based on what they've built in. But in regular expression, we actually can turn this first parameter into code. And so what's happening here is the caret, if you go back to the little cheat sheet, caret means this is the beginning of line. It's a virtual character that matches the beginning of line. It's like from that starts at the beginning. So from at the beginning does match, and from in the middle does not match by putting that little caret there. Same thing, line is what we're searching, and then from is what we're, caret from, line at the, from at the beginning is what we're looking for. And so again, it does the exact same thing. It only prints lines that have from : as the first character in the line. So the difference is we look for a method, and the other one is we program the regular expression. So we're going to run out of methods in the string class long before we run out of things that we can do with regular expressions. And so a couple other special characters that caret matches the beginning of the line. So caret matches the beginning of the line. This capital X matches itself. Dot is a wildcard that matches any character. And then some of the characters in regular expressions modify the immediately preceding character. And so that says, look for a line that starts with X and then has many characters. That's with these two things. 0 or more characters followed by a colon. And so you can see that it's this sort of like expanding stamp. It's like, oh, there's an X at the beginning of the line, that line, it looks good. I got some characters here and then I got a colon, that's good. So this is an X, some characters, and a colon, check. X, some characters, and a colon, check. X, and these things, away we go. And so you can, that's what's going to match. And so you can see how some of these characters are special. Again, go back to your cheat sheet. Some of them are special and some of them are actual characters. And this colon and X are just, they're not special, they're just the characters. Okay? Now, sometimes you want to be a little more clear on your match. So let's take a look at these lines that match that particular thing that we just did. So we have these two, x-civ colon, x-d stam dash result, like these are from mail messages. And then one of the mail messages has a line in it that says x-plain is behind schedule. And this matches. Is that what you really wanted? And so what we can basically say is, because this is an X, this is some number of characters, and that's a colon, it matches. It has to match. That's this rule applied to this line results in a yes. It does. And so how can you be a little more clear as to what you want to match and what you don't want to match? So we can write code. So now what we're going to say is we want to match the beginning of the line, and we want to capital X, and we want a dash. So now we're going to match those first two characters, X dash, at the beginning of the line. Caret X dash says first two characters of the line must be X dash. Now we have another special character. Again, refer to your cheat sheet. Backslash capital S means a non-white space character, right? Any character other than white space. And then plus means one or more times, one or more non-white space characters. That's what this whole thing says. One or more non-white space characters, and followed by a colon, which is just a character. So now we have X dash followed by one or more non-white space characters followed by a colon. X dash followed by one or more non-white space characters followed by a colon. Here we have X dash followed by one or more, whoops, there's a space there. And so this doesn't match. Even though there's a colon there, it means that between the dash and the colon, you can only have some number of non-white space characters. So this is a no, it does not match. And so you just can, if you didn't want to match this, you then sort of create a more precise, we could even have a thing that said, I want X dash with an uppercase character, uppercase letter, if you wanted to. And so there's all kind of fine-tuning if you sort of learn the structure that you've got to do. And so that's kind of the matching, where you're taking a whole line and taking this template and deciding if the template anywhere in that line matches. And now what we're going to do is use this to actually pull data out of strings using the regular expression library. So now we're going to move from merely matching to matching and extracting. So we're going to say, hey, I would like to not only have you take this template, this little pattern, the string pattern, regular expression pattern, run it across the line. I want you to give me all the ones that match, and I want a list of those. And that's what we're going to use the find all. So search gives a true false. Find all gives a list of all the strings that match. So if there's 4 of them, you'll get 4 things in the list. If there's nothing that matches, you'll get an empty list. So let's take a look at what we got going here. So instead of calling search, we call find all. We still pass in the string that we're looking through, and then we have our little template pattern. And this is a new bit of regular expression. Any little bracket operation, square bracket, is one character. That's just a character, but then there in between here is a set of allowed characters. So 0-9 means a single digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. But that's really one character. And then we have, so that's one character. And then when the plus applies to that, which means if we look at this whole thing says one or more digits. That's the code we write in a regular expression that says one or more digits. And we're just going to use that in our regular expression by itself. So we're going to look for any string that's one or more digits and pull it out and give it back to me. So it's going to look. So that's my little template, stamp, 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 stamp. Oh, got it. stamp, 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 oh, got it, stamp, 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 got it. So what we get back after we ask find all to find all of the one or more digit strings is 2, 9, and 42. So it actually parsed it, it split it, it found all these things and said, I found them all for you, and here they are, 2, 19, and 42. So it's a list of 3 strings, because that's how many it found. Now it might have found none, and we would have got an empty list at that point, but it found some. Okay, so just as an example, you know, we did this thing, we get 2, 19, and 42, but if I said this, that basically is an uppercase vowel, A, E, I, O, or U, so that's one letter, and that's one or more. So it's saying, you know, something like A would match, E, I would match, O would match. But if you look now, it's saying, okay, I'm looking for one or more, minimum one or more uppercase. A, E, I, O, U is a set of characters, one or more uppercase letters. And so it's like, look, do you find, oh, there's an uppercase, but it's an M. No, 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 no uppercase, no uppercase, no uppercase, no uppercase. Found nothing, did not find anything. And so it gives us back an empty list. And so it's like, find all the things that match this, and the answer is none matched. Here's your list of nothing. Okay, and so you have to check. That's how you have to check even if you got something, because it's not going to return you false. It returns you a list with no items in it. Now, the way it works, like I said, it sort of is taking this template and stamping it across the line, stamping across the characters. Now, there's a behavior that might not be intuitive you at the very beginning, but the notion of what we call greedy matching, and that is when it can match more than one possible string, overlapping string, it chooses the largest overlap of the overlapping strings. And so the easiest way is to show this with an example. And we're saying, I want something that starts with an F with one or more characters and ends with a colon. So that's my little stamp, that's my template. So starts with an F, good, that's good. One or more characters, da 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 da, have a colon. So that could be from colon. That would match. But look, I've got another colon here, and this is just continuing on with one or more characters and this. So the question is, do we get this or do we get this part, right? And the answer is, with greedy matching, is we get the larger of the two. Okay? And so what you get back is somewhat counterintuitive. You get the whole thing as the match, from colon using the. We could have got from colon, but the reason it picks this is this one's longer. So anytime it has a choice, it picks the longer one, and that's what greedy is, meaning it'd probably be better described as larger or tending toward the longest string or something like that. So you can, of course, suppress this behavior. Like everything in programming regular expressions, you simply add another character. And so now it's going to say, I would like to start with letter F, any character, one or more times, and then this question mark, this is still one little thing, non-greedy, okay? And so that just says do it not greedy, which just means that it prefers the shorter of the strings. And so now it could still match this string or this string, but because it's been told to not be greedy, it chooses this string instead, and that's the string that we get. And so that's the not greedy, and you just add the question mark after the asterisk. So it's usually an asterisk question mark or a plus question mark, though that's a two thing. That's 0 more characters non-greedy, and that's 1 or more characters non-greedy. Actually, most of the time, it seems to me that the non-greedy would be the more reasonable default, but that's not how it is. Greedy is the default, and non-greedy is optional. Now, we can play some more with this stuff, okay? And so let's take a look at this little example where we have a non-blank characters, \S, 1 or more of those non-blank characters, followed by an @ sign, and then again 1 or more non-blank characters. So this is looking for strings that have an @ sign with non-blank characters on both sides. This is an example of where it sort of comes to this @ and it goes this way, and it does it in a greedy manner. If you told it to not be greedy, it would give you these 3 characters. But we're telling it to go greedy, so it goes all the way to here and stops at this blank, and then stops at this blank. And so that's a nice little thing. Find the @ signs, go to the first blank, and pull that stuff out. And so that, with one little match, you've pulled this thing out. Now, of course, we've done that before with other techniques. So that's just another way to pull stuff out. Now, if we get this whole thing, but what if that's not exactly what we wanted? We can tell, we can give it a matching string that's different than the extracting string by adding parentheses. And so here's another example where we basically say, this is our string. We want to match from at the beginning, followed by a space, followed by, ignore the parentheses for the minute, one or more non-blank characters, followed by an @ sign, followed by one or more non-blank characters. So this is also going to, if there's no from, it's not going to be looking for that, right? So it demands the from is here, so it matches that, and the space is demanded as well. And then it says, oh, non-blank characters, great. I got an @ sign, great. Non-blank characters, oops, stop there. And so this is what's going to match. Now the key is that we don't actually want that back in our extraction. What we really want back in our extraction is this part right here. So what we do is we put parentheses in. Parentheses are code, they're code in the regular expression world. Parentheses say start your extraction and end your extraction. And so when you do this with a parenthesis, when you do it, without a parenthesis, you get the whole from, right? Without a parenthesis. Oh wait, no, okay, that doesn't have the from in it. So, but if you do that with the parenthesis, you match the from, but you only get this bit to come out as well. So you can add this to make the matching part more precise, but without changing what you get returned, and you specify what you want to get returned with the parentheses. So next I want to show you just a couple of different ways to use these newfound skills. So now what we want to do is use some of these newfound skills in some more practical applications of regular expressions. So let's go back to the way we first tore apart strings and look at the situation where if you recall, we just wanted the host name, right? This is an email address and we're interested in the host name. So we have this string and we go find the @ right? The find looks up and tells us the @ is at position 21. And then what we do is we say, okay, let's look beyond there to the space, and that tells us the space is in position 31. And then we're saying we can extract starting at beyond the @ sign up to but not including the space by saying @pos +1 : space position. And when we get that, now we have to have a thing that decides to only look at this on from lines, but then it can print out the host that is extracting of this information. So that was one way that we did that, right? One way we did it. The next way we did this was the double split pattern, right? So we said, okay, let's take this line, let's break it into words based on spaces. That's what words is. So that's 0, 1, 2, 3, 4, 5, 6. And then we know that the email address on lines that start with from, space, is the second one. So we pull out email address, which pulls this bit out into email. And then we're going to split that again based on the @ sign. So we're going to split this part again based on the @ sign. So it splits right there, and then this becomes the 0 and 1 in pieces. And then pieces sub 1 is that host. And if we print that out, we get the host. So that's the double split pattern. Nice thing about that is you don't have to keep track. The little +1 is kind of annoying to use the space position. That previous one, that's just hard to remember. It's just, I've written this code way too many times in my career, and I've made mistakes, and I have to debug it every single time, and I print all these numbers out. I'm like, did I get it right? Oh, I did it in Python, I did it in Java, I did it in C. Wait a sec, I did it differently. And so this is a lot cleaner. I mean, I can write this every time, and I know it's going to work every time. I barely even need to test this code because it's so obvious. So double split is another way of extracting stuff. But if we look at this thing with the regular expression, we can say, oh, okay, let's use a regular expression to do this. So we'll start looking through the string. We'll start by saying, hey, let's look until we find an @ sign. Then let's start extracting with the parentheses. And then once we have found the @ sign, let's look for non-blank characters. This is a set of characters. This caret as the first one means not a blank. So that's another way to do non-blank. Not a set of characters which are everything but blank. That's what this little bit is saying. Star means 0 more times, which means it's going to run until it finds a blank, which is going to stop it. The greediness is what keeps pushing it, right? This is a greedy match. That asterisk is greedy because there's no question mark after it. And so that does go and starts at the @ sign with the parenthesis, goes to the space, and that's the end parenthesis, and that's what prints out. Now, Y is going to be a list that's a one-item list that has the string in it that we're looking for, but you can just go sub-0 to get that guy right out of there. Okay, so that's sort of the regular expression version of it, but we can make this a more fine-tuned thing. So we can say, look, we also want to pick the line, and we want to know if we don't get that line, we want to skip it. If we do get the line, we want to extract the data, and we can do this all in a single regular expression. So again, we say start from the beginning of the line, and it's got to be a from, followed by a space, and then followed by any number of characters, dot star, followed by an @ sign. So this has to match. We see a space, then we're going to have any number of characters, and then we're going to see an @ sign, and then we're going to start extracting, and then we're going to go non-blank, 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 up, blank, and extracting, and out that comes. And this has the advantage of the previous one in that makes it much more precise. If we look at the previous one, while it works on good lines, it might actually trigger on lines that we actually don't want to see. So this allows us to refine it so it only actually does this to lines that we care about. So it's sort of both an if statement and a splitting, extracting going on all at the same time by having a bigger string that we're matching than we're extracting. It's a way to kind of clean up your data. So here is a simple program that we're going to just put all this together and actually accomplish something. And so we're going to read through and look for lines in a file that have this form. And we're going to extract this number, and then we're going to compute the maximum of this. Okay, and so we're going to extract this number and then convert it to a float and compute the maximum. So, we're going to open a file, we're going to write a for loop, we're going to strip. So we're going to do this for every line of the file, but the first thing we want to do is not get line. We want to discard all the lines except ones that have this. So our regular expression is look for lines that start with x-dspam-confidence : So that's a pretty strong match. If that's not there, we're not going to get anything. And then there's a space, and then start extracting, and then go as long, one or more digits and dots, that's a single character, and that's one or more, and then stop extracting. So that says start extracting, greedy, stop extracting. And so that's what we're going to get. Now, if the line doesn't have this, it means missing in some way, whether it's this prefix or this number. If the number's missing, it's going to fail too. We're going to get back a list, an empty list. So the first thing you have to do is check to see if you actually got a match. So you say if the number of items in the list, len of stuff, is not equal to 1, continue. And so this is the skip all the lines that don't match. Skip. So there could be thousands of lines that don't match. But then when this match hits, it's going to come down and fall through. Right? So that most of the lines will skip up, but then when we actually get one, and we know instantly that we've got one, and stuff sub-0, because that's what we extracted, is this number. And we can take the floating point of it, we append it to our list, we made a list to store them, that runs, the list grows, and then we just say what was the largest one. And so you can run this and see that. We have an escape character, and the whole idea is sometimes all these little special characters that make a lot of sense to us, we actually want to search for it. So what if we want to search for a $? Well, we just prefix it with the backslash. And that just means this is a real $. So $$ is a real $. So this says, I would like a $, followed by one or more digits or dots. And so that's going to match a $, followed by one or more digits. Dots are okay. This is a set, remember. 0-9 or dot, that's a set of the list of legit characters. This is a range of characters that's a shortcut to how to make the set. You could make it be 0, 1, 2, 3, 4, 5, 7, 8, 9 dot, or 0-9, and it assumes that. And that's one or more. So then it stops because this is a space. It's greedy matching. Then it pulls this out. So that's kind of why greedy has to be the default, because otherwise if it wasn't doing greedy matching, oops, come back. If it wasn't doing greedy matching, it would, if it wasn't doing greedy matching, it would stop here because it would find a $sign. Non-greedy would find a $sign and one character, and then it would give us $1 rather than $10. So, in summary, regular expressions are a cryptic but powerful language, and they're an acquired taste. I bet eventually you will find them fun, even though on your first impression you might not think that they're so fun. Welcome to Networked Programs. This is Chapter 12. Now we're going to learn a little bit about how we talk to resources on the network using Python. Now, this is a really quick introduction to how the network really works. I have a whole book that I wrote. It's also translated into Spanish on how the network works, starting at the very lowest layer, packets and everything, right on up. And it's actually really easy to read. I wrote it for a high school audience. It's a short book and pretty easy to read. So if you read that book, you will understand that there is this layered architecture, the TCP architecture that sort of runs our network. At the lowest layer, that on one side here, this is your computer and this is a server computer. And if you sort of want a web page, it goes across the network, does this like 15 or 20 times, then it goes up into the server, reads the data, and then the data comes back, 15, 20 hops for the packets, and then it's shown to you as what you see. And so that's how it works, and there's these layers that we're not going to talk about in this section, but I talk about in that book. The layers of the link layer, which talk about how to get over one hop, the internet layer, which talks about how to construct, say, 15 or so hops to get packets back and forth. That's the sort of lower level bits. We're going to start at what we call the transport layer, and that's the layer where your computer sort of assumes that it can make a phone call to another computer, another process running on a program on this computer, talks to a program on this computer, and then it kind of comes back. Okay, and so we're gonna leave this alone. We're going to ignore it. We're going to assume that there's this nice reliable pipe that's going from point A to point B, and what are we going to do with the pipe? But if you're interested, take a look at the book. So we're going to start with a pipe, some kind of a connection. We have two processes, process, and we have some kind of a connection between them. And it is a connection that we can both use to talk and to listen. In nerd terms, we call these things sockets, and that is one process running on one computer, another process running on one computer, another second computer connected through the internet somehow, and one computer speaks into that socket and it comes out, and the other computer returns something and it comes. And so this is a bidirectional protocol of data, which is a series of, in effect, data phone calls between applications. So the application might be on your side, this might be your browser, Chrome, Firefox, Internet Explorer. On the other side, this is a web server. Might be Internet IIS, Internet something something from Microsoft, or Apache, or Java Tomcat. There's another program, and you are making phone calls between these programs. Now, in general, these servers here stay up all the time, and you sort of just can make a request when you feel like it in your program. But that's what we're going to do, and this is what we call a socket. So that little connection, that phone call, that data phone call, is what we call a socket. Now, you have to decide which of the systems you're going to talk to, and then which of the services on those systems, or which process. And so we have this concept called port numbers, and they're best thought of like extensions on phones. So one organization has one phone number and it says, please enter the extension of the party you'd like to talk to. Well, that's kind of what ports are. They're like, here is, I'm a server and I'm connected to the internet. Please enter the extension of the process that you would like to talk to. And so, for example, there might be processes running on various computers, and so the email is known to hang out on port 25 or extension 25. Insecure login lives on port 23. Insecure web lives on 80, and secure web lives on 443. And there's a couple of different protocols. Say if you have your mail stored on Gmail and you have a local mail client, say like Thunderbird or Apple Mail, that talks a protocol to pull that mail across, and those live on various ports. So these ports are those extensions, and by convention, we have standards that tell us what to roughly expect at those ports. So when you're talking to port 80, you expect to talk to a web server or an HTTP server. If you're talking on port 23, you expect to talk to a Telnet server, and on and on and on and on. And so these are the extensions, the typical, commonly used default extensions for various network application processes that are serving us data. Now sometimes you'll go to a URL and you'll see in that URL there's a colon and a number. That means it's a web server that's running on a port other than the official 80 or 443 port. Now in Python we can talk to these sockets, right? We can just talk to them, and it's really easy, surprisingly easy. We have to import socket because that's a library. It comes with Python, but until you can use it, you can't use it in your program until you say it. And then you basically in the socket library you call socket function. That's what that syntax is saying. You're making a socket. Now the key to a socket, it's sort of like an unopened file handle. It's half of a file handle. It's an outward looking thing that's not yet connected. These parameters, you're just going to type them in. This says we're going to make a socket that goes across the internet, and it's a stream socket, which means that it's a series of characters that come one after another rather than a series of blocks of text. There's another kind that's harder to deal with, but we're going to do this. So this, don't worry about this line. Just know that this creates a socket but does not associate it. The very next line, we get back a socket object in this variable that I'm storing in the variable mysock. And then when you want to make a connection across the internet to the far end, you say, oh, hey, dear socket, extend yourself across the internet. Make the phone call to this host, data.pr4e.org, and on that port 80. So that's making the phone call. This is like the phone number, and this is like the phone extension. So we haven't sent any data yet. We have simply rung the phone of a process, hopefully living on port 80. If it's there, great. This might blow up. This one here won't blow up, but this line here could blow up. If there's nothing sitting on that process, it would come back and say, oh, you tried to call, you got no answer. That's a legitimate thing to happen. Maybe you don't have a network connection, or maybe that service is down on that server, or the whole server's down. But so it's kind of amazing that we're sitting here in Python, and in 3 lines we have probably 500,000 engineers have built this thing called the internet, all these protocols and all this software, and we just made use of it in 3 lines of Python. And I guess this is one of the reasons that people absolutely love Python. Absolutely love Python. So now that we have a socket, we have to ask ourselves, what kind of data are we going to send, and then what kind of data are we going to expect to receive across that socket? So now we have a socket, we are going to talk about what we're going to do with it, right? So the socket basically functions at this level. Your application is saying, make me a socket, which is sort of this endpoint, and then the connect actually connects to an application on the far side. And there's a port involved, so that might be port 80. And this is the far host, and that could be www.py4e.org or data.py4e.org. Okay, and so the socket is solving this, and the question then is, what are we going to send and what are we going to expect to get back? And that's what we call the application protocol. So we know that these two have made a phone call. And it's no different than making the phone call and saying, you know, hello, right? And everyone knows that when the phone rings and you pick it up, you're supposed to say hello. And that's part of our protocol. So who talks first, right? So the dominant protocol that we use in this section is the HTTP protocol. The key is hypertext transfer protocol. It's dominant. It's really easy to use. That's why I use it as an example. But realize that there are many others like mail and file transfer and remote login and all kinds of other protocols. Each is a different application protocol. They all use sort of sockets at their lower level. But then on top of that, they layer the rules of the road for retrieving hypertext web pages, and we have used these for all kinds of other things. So the protocol, like I said, is like who answers the phone first, what do they say, what happens if the person doesn't answer right, can you hear me now, those kinds of things. And it's a real simple thing, and all you really need to do is, so that both sides can agree, you have to write a thing that's like the rules in the middle and say, okay, everybody, as long as we all do this, we'll be fine. It's as simple as picking on which side of the road the cars can drive on. It works fine no matter which side, but if each car randomly picked, it would be really kind of a mess.
So if you look at the typical URL, and this is one of the things that the web innovators in 1980 really invented that was wonderful, and it seems second nature today, but in 1990 it was rather revolutionary in that these uniform resource locators included in themselves a protocol, the host to connect to, and the document to retrieve. So this is one of the clever ideas that the web came up with, because we used to have to pick a program like FTP or Telnet or whatever, SMTP, then we had to go to the right host, and then we had to talk to that host a certain way. So in HTTP, it's a really simple protocol invented in 1989 and 1990 by Tim Berners-Lee and Robert Caillou at CERN. And they created a protocol that we have grown to know and love and use for way more than retrieving documents, as we'll see in the upcoming chapters. So we're going to talk a little bit about what happens when you click on a page that has a link. Now, there's all kind of fancy stuff that can go on, but this is the basics. And so let's just imagine for the moment you are sitting looking at a web page, drchuck.com/page1, and inside that there is a hyperlink. It is a indication that says when you click on this page, go to a different page. And in that you see the name of the page that you're supposed to go to. So we click on this link, and that is a browser. This is an application, this is a process or an app that's running on your computer. This is the browser, okay? And when the browser sees the click inside your computer, then the browser makes a connection to port 80 on the web server, drchuck.com, and sends the request. This request that it sends is precisely specified by a standard, which we will see in a second. Then the web server does some magic work. Oops, let's go back. Then the web server does some magic work in here, reads some files, runs some code, does whatever, constructs an answer to our phone call, and sends it back. And it sends, in this case, back a web page in the format of HTML, the hypertext markup language, which is different than HTTP, which is the protocol that we're exchanging. HTML is the format of the document we're getting back. And in this has an anchor tag, href, and the end of anchor tag, and some highlighted text. And now your browser gets this back and then renders it according to the rules of HTML and CSS and JavaScript, etc., parses it, and then makes a pretty web page. And this web page happens to have a link back to the first page, and if you click there, it will do this over and over and over again. And that is the request response cycle. And that's governed by a series of internet standards. These are standards that were built from the 60s, 70s, 80s, and 90s and continue to this day by a group called the Internet Engineering Task Force, or IETF. The documents they produce are called RFCs, which stands for Request for Comments. The word RFC is kind of like a sort of joke, as it were. They're trying to be kind of funny in that, funny is not the right word. It's ironic in that they're trying to say, even some of the protocols of the internet that we've used for several decades, they're always interested in improvements, and that's what the RFC stands for, and they're all named RFC-whatever. And if we were going to cruise around, we could find some various RFCs, and this is RFC 2616. It might have been revised since then, but this is like a document, and this is what they look like. Hypertext Transfer Protocol version 1. And so you're reading this document, you're going to write a browser, and you want to talk to the application protocol that is HTTP. This is one of many documents that helps define what HTTP is. So if you look down and said, oh, here's what a request looks like. This is how I'm going to get a document from the server. And you keep reading and you keep reading, and it says you're supposed to have the request method with a space, with the request URI, the request method with a space, with a URI with a space, the HTTP version, and the carriage return the line feed. That's what it's saying. And so it looks kind of like this, right? We say get the document followed by a space. There's got to be one space. You do two spaces, and it's going to be quite frustrating, okay? And so this is an example that you can run on a number of on Linux operating systems and Macintosh operating systems with no changes. If you install Telnet on your Windows box, you should be able to run something like this as well. So Telnet is a program that we used in the old days
It used to be how we logged into servers, but because it doesn't encrypt your data back and forth, we don't use it anymore. But it basically is a program that can open a socket to a host on a port. And I'm saying telnet to this host on port 80. And at this point, I am connected, and whatever I type on my keyboard is going to be sent to that server. Now, if you're doing this, you probably want to cut and paste this really fast, because if you take too long, most web servers will be like, you're a human. I don't want to talk to humans. I want to talk to programs. So remember to type this fast enough, and then you have to hit enter twice. So you have to have a blank line here. Just type this exactly as it's shown, and then you will get back the server. If you do it right, the server, and the server is properly configured, the server will give you back some headers. And this is metadata about the document you're going to get. For example, it's saying it's got text/HTML, which means that the remaining stuff is going to be in HTML, hypertext markup language. It has a blank line, and then the actual document, and then the connection is closed. And so if you do this, you can set this up in a way that you can run this on your own computer and in effect hack through the back door a web server. Now, you can't hack the secure web servers, and mail servers used to be easy to hack, but they're harder to hack now because they challenge you for information. But part of the reason I'm so obsessed with the command line is this is how real hackers work, and they know how to talk some of these protocols more directly. And so we think of this beautiful, sophisticated application talking to some other thing, and it's all pretty, and we got wonderful clicky buttons and nice usability. But the reality is, like in the Matrix Reloaded here, the kinds of things that really talented hackers are doing use command lines, and they really know what's going on, and that's how they do it. They understand what's going on better than the developers of the computers that are trying to be resistant to the hacking. So I come from a long line of using the command line, and that's why I encourage you to use the command line in this course. So the next thing we're going to do is we're going to go up into the application layer, and instead of typing those commands by hand, we're going to actually send them from Python and write a very simple Python web browser. In this section, we're going to write a web browser using Python. So we've already got a socket. We know how to write a socket. In the previous section, we played with the protocol and used Telnet to do it by hand, and now we're going to do it in Python. And what you're going to find is it's not that hard. So here we go. So the first 3 lines of this program: import socket, make the socket. Remember, the socket isn't really got the connection. So when you make the socket, again, we're going to make a stream-based socket, and it's suitable for going across the internet. The connection, it's like ring, phone call, connect to data.pr4e.org and port 80. And so that basically says extend the socket across and connect to a web server. And so there's got to be a piece of software running, and this will blow up if the software is not running. Okay? So then, now we've got a phone. We've made a phone call. Now, whether or not the remote side says hello or not is up to the application protocol. And in this case, the web servers say nothing, and they wait for you to talk first. So we're the web browser in this case, and so we're going to talk first. And we know what, because we read the documentation, we know that we're going to send get blah, 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 space, blah, 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 ht1, and then 2 new lines. Return, return. Remember, you had to have a blank line. We'll talk a little bit about this encode. It's preparing the data to go across the internet. And then we say send it. And so this basically takes that little string and sends it across the network. And then this piece of software is waiting for it. And then the software goes and reads a file or does some other stuff, and then it starts sending us data back, which we can then choose to receive. So now I write a real simple loop. We're going to receive these things 512 characters at a time. So we're going to loop through, receiving 512 each time. And if we get 0 characters, that means it's end of the stream. The stream is closed. And if you look at the little example from the previous one, you saw connection closed. When the connection is closed, we get an indication that it is because we ask for some data and we get 0 data. Otherwise, if there might be more data, this will wait. If the network is slow, you'll see, if you do a print statement in here, you will see that this will pause from time to time on a really slow network. If your network is fast, it'll just go blank and it'll be so fast it won't matter. But this is how we go. So this is basically until the entire socket, until the socket is closed, we're going to read this data. And because this data is coming from the outside world, we have to decode it before we print it. And then when we're all done, we break out of here and we close the socket. So literally, that
is an entire web browser written in 10 lines of Python. And again, this is why everybody loves Python. So this is what this program will show if you run. The get is sent. It looks exactly like doing it by hand. You get some headers. Again, this is metadata that tells you something about the file. In this case, one of the important things is what kind of thing is coming next. There's always a blank line as a break between the headers and the actual data, the metadata and the data. And then here is the actual text of that romeo.txt file. And then it's going to run this, going to print data.decode. All this is coming from the print statement. If you were going to parse this, you have to know that you're going to read the headers up to a blank line. The blank line is your indication as a software developer that the headers have stopped and the actual text begins, and you know the syntax. This actually could be a JPEG or a PNG or some kind of image, right? And this data would here look like blah. So if you type this and you change that code to actually go retrieve a JPEG URL, gibberish will come out, okay? And so that's exactly what you will see. And so now you have built a very simple web browser. Next, I want to talk a little bit about what happens when characters transition from outside your computer, from inside the computer in strings, out across these sockets to servers and then back.
Hello everybody, and welcome to some worked sample code. If you are interested in the source code, you go to materials and download this sample code.zip. I have this downloaded. It'll be in a folder called code 3 on my computer. This is where I'm at. I'm in the code 3 folder, and this has a ton of bits of code here. So if I do an ls, you'll see I got all these files here, and so we'll just leave those there. And so this is the one I want to work through right now, is this socket1.py code. And basically what we're doing here is we're simulating what is going to happen in a web browser. And the cool thing about the HTML, the HTTP protocol, is that we can do this by hand. And I'm actually going to hack this HTTP protocol. This is going to go to data.pr4e.org and retrieve a document. And so I'm going to do Telnet now you can do this on a Mac and Linux, and if you put Telnet on a Windows box, you can do it here, data.pr4e.org. And I want to talk to port 80, and the port 80 is a different port. It's a non-standard port, but what we're doing here is talking to the HTTP port. And so I'm going to be able to hand send commands to the web server and retrieve a document. So I'm going to cut. I've already copied this string, this get http romeo.txt. I'm copying that into my buffer because if I wait too long, this won't work. So here I go, and now I'm going to type that, and I have to hit enter twice. And that literally was the HTTP protocol. What I typed there was the HTTP protocol, and the web server responds with some metadata about the document. How much data there is, the kind of data is there. A blank line separates the header information from the body of the document. If I was to go to this in a browser, right there, you would see, and if I turned on Developer Console and I went to the network, let's make this a little bit bigger, you would see that it retrieves this file romeo.txt, and it gets back that it shows us the headers, and it shows us the response. And so this is all the same way of doing the same thing, and that is how to do the HTTP protocol. Okay? But now we're going to do this in Python, and so here's the code we're going to write. So we're going to import the socket library, and we're going to make a socket. Now this doesn't actually make a connection. Think of a socket as a file handle that doesn't have any data associated with it yet. And then what we're going to do is we're going to reach out and connect that socket to a destination across the internet with the domain name of data.pr4e.org. And the second parameter in this tuple, this is a function call with a single tuple as a parameter. And so tuple sub 0 is data.pr4e.org, and tuple sub 1 is the 80, which says I want to talk to port 80. That could fail. It will make the connection, and And if the port 80 is there, away it goes. And then we're going to actually send the HTTP command. So get, this is the HTTP rules, followed by an end of line, followed by a blank line. So you saw me do this. This was what I typed here, and then I had to type a blank line. Now, if you want to go read the RFCs for how to do this, you can figure this out. So the only other thing that's kind of weird here is we have to add this dot encode. And that's because there are strings inside of Python that are in Unicode, and we have to send them out as what's called UTF-8. And encode converts from Unicode internally to UTF-8. So this command is a set of UTF-8 bytes that we're then going to send. It still has that same set of characters in it, and now we're going to send it. And that's after we've made the connection, we're going to send these two things, and then we're going to wait. And my sock is like a file handle at that point because it's been opened and we've sent data. The HTTP protocol told us what we had to send and the fact that we did have to send it. So now I have just a simple while loop, and I'm going to ask up to 512 characters and receive up to 512 characters and get that back. If I will know that this is the end of file if I got no data back. So if the length of the data, the byte array that I got back is less than 1, then I'm going to quit. Otherwise, I'm going to print the data, and I'm going to use this decode, which is kind of the opposite of this encode. What I'm getting is UTF-8 encoded data, most likely, and decode basically converts it to the internal format called Unicode that runs inside. And so this is going to run a bunch of times, pulling in the blocks, basically 512, up to 512 characters at a time, printing it out, and then when it's all said and done, we will close that connection. And so it's not too exciting. Python 3 socket 1.py, and you'll see that it's just going to, Python is now going to do what I did by hand. Now, of course, the interesting thing is these are all in strings, right? And so, this way we could write code that does stuff with this. But all we're really trying to do in this particular situation is show how you open a socket, send a command, and then retrieve the data. Okay, so now it's time to teach you a bit of complexity about text processing. Up till now, we've kind of been ignoring the complexity of text processing. Everything that I have been doing, most of what I've been doing is in ASCII, the Latin character set, the character set that, United States, Europe, lots of Western civilizations use this character set. And if you go back to the 1950s and 1960s, we were happy to have one computer, and we didn't care what the character set was as long as what you typed on the keyboard came out on the printer. The internal representation didn't matter. And as the 70s and 80s came along, certainly 70s, we needed some interoperability, and so they standardized on a character set, but they standardized on a character set certainly in the West that did not represent anything. And so if you look at this at this sheet, basically what it's telling you is for the various characters, there's some non-printing characters, white space, non-printing characters, and then here's some printing characters like the and key, the 0, and then the uppercase characters, and then the lowercase characters. And there's 128 of these possible values. And there are nothing even for Spanish or French in here. And it's also why, by the way, uppercase letters in Latin sort lower than lowercase letters, and we saw that in some of the string stuff. And what these do is it maps and says, okay, and a lowercase a maps to the integer number 97, which in base 16 is 61, and in octal it's 141. But in binary, it's 8-bit numbers, and so these are 8 bits, otherwise known as a byte. And they're very efficient. Like when you buy a disk drive, it's megabytes or gigabytes or whatever. That's how many of these kind of characters it can store. But unfortunately, this doesn't work for more complex characters. You can figure out these numbers inside of Python by using the ord function. And so you say, what is the ordinal, or the numeric representation of the uppercase h, lowercase e, and new line is a character as well. And so like 10 is the ordinal position of new line. And this actually has to do with sorting, so that lowercase e is higher than uppercase h. And that's just because in the simplest of sorts, we just sort them numerically. So new line, if you go back to the previous little sheet, new line is this 10 right here. It's that 10, which is a line feed, and that's a 10, and that's why when we print new line out, we get a 10. And so again, in the early days when strings were simple, we just represented them as 1 byte per character. But the problem is that, you know, as we have gotten more complex, and in today's modern world, it's simply unacceptable to say that the only thing computers can understand is ASCII. And so this leads to a from the simplest of character sets to a super complex character set called Unicode, which basically is billions of characters, potential billions of characters for every language and every character set. And because there's so much space in Unicode, it's easy to take very small variations of characters and give them a space. It's so large that you can have you can have pretty much any character that you want. So that's Unicode. The problem is that if we sent Unicode across the network, it would be way too large. It'd be this UTF-32, which instead of being 8 bytes per character would be 4 bytes per character. And so it would take all of the data that we build and make it 4 times larger. And it'd be very difficult. And so what they've come up with is ways to compress this. And UTF-16 is this weird thing. UTF-32 is really sort of the full Unicode pretty much. UTF-16 is a subset of Unicode. It's used in some countries, but the best practice for moving data across the internet or in a file that you're going to move between computers is what's called UTF-8. And so what happens is that UTF-32 is fixed length. ASCII is one byte. UTF-16 is 2 bytes, UTF-32 is 4 bytes, and UTF-8 has dynamic length, meaning that it is 1 to 4 bytes, and if it's only 1 byte long, it's perfectly compatible with ASCII, meaning that an ASCII file is also a UTF-8. And so here's this little sheet, and it's not critical that you understand this graph too much, but basically as time passed, 2000 internet's coming, now 2014, pretty much overwhelmingly the documents on the internet that you might retrieve are UTF-8. Now, so UTF-8 is the recommended practice, and it's sort of a compression of UTF-8 can represent all the things UTF-32 can represent. It's just a compression of it so that, and with an overlap of ASCII, which is awesome. It's what you want. I don't even talk anymore. So in Python, we have always had sort of 2 ways of representing strings. In Python 2, the normal string was a byte string, was an ASCII string, was a Latin string. And if you wanted to represent Unicode, there was a separate kind of object that we had. And so you would do that. And in Python 3.0 or later, one of the main features of Python 3 was to make Unicode and string the same. So that means inside of Python, when you have a string variable, it's a Unicode. Whereas inside of Python 2, it was a byte variable. And so now we have this notion separately in Python 2 and on Python 3 where we have byte variables. And so byte variables are, in effect, an array of bytes. So if there's ABC, that means it's 3 bytes. It's 3 bytes long. Whereas a string might be a 3-character string might be anywhere from 3 to 12 bytes long. So Python 2 had bytes and strings that were the same. Bytes and strings are the same, and Unicode is weird. And in Python 3, strings and Unicode are the same, and bytes are weird. Okay, and so that's what we've got to deal with. And there'll be times when we get bytes from APIs. When we call things, we have to then figure out what kind of thing those bytes contain, because the bytes might contain ASCII, they might contain UTF-8, they might contain various things. And so internally, all the strings in Python 3 are Unicode. Most of the time, if you're inside the program or reading and writing files, we just work. And that's why we haven't mentioned it. But now that we're talking over sockets, and we're talking to the sort of random world out there, we have to be a little more aware of the data we're dealing with. Now, the good news is 98% of the time, or 95% of the time, it's UTF-8, which might also include ASCII, and so it's quite nice. But we have to be aware of this. And so if we are going to take data that comes off of the network in the bytes, then we have to make sure that we interpret it or decode it and in the right way so that internally the strings, which are Unicode, are properly represented. And so that's why when we read data in from a network connection like a socket, we have to say, hey, decode it. Now there's a couple things going on at that moment of decode. And so this is where we're doing it. We see this, we have to manage this in this code where before we send this stuff, we're going to encode it, which takes a Unicode string and turns it into UTF-8 bytes. There's actually a parameter here that you could do it different than UTF-8, but no one ever does. You might have to for certain situations, but so that says that we're going to encode this into UTF-8 before we send it, and then when we get something back, before we print it, we're going to decode it. And that's how this ends up working out. And if you look at the documentation, you will see that sometimes it says it's a string or it's bytes. And so you take a byte array and you decode it to get a string, and you take a string and encode it to get a byte array. And so that's what we're doing. So you can think of the process as this way, and that is the network has these UTF-8, mostly UTF-8 resources, not ASCII. If it's ASCII, it's okay. So you read with the receive. So this receive here pulls data, or well, we have a Unicode string. Let's start with the send. So up here we have a Unicode string. That's a Unicode string, even though there's no special characters in it, no Asian characters or French characters. That's a Unicode string, and before we can send it, we have to send it in UTF-8. If that had Asian characters, it'd be okay, and that would be set up just right so that the UTF-8 would be right. So we encode it first, and that's this CMD. This is now bytes. Okay, CMD is bytes, and then we actually send the bytes, and that goes across the network. We get back our thing, and we receive into data. Well, data is bytes, not string. It's bytes. We can say how big it is. Functions kind of like a string, and it has len, except that it is 1 byte per character, which means some of it might be UTF-8. And then all we have to do is say decode. Again, you could, if you were dealing with a situation where you weren't expecting it to typically be UTF-8 or ASCII, you could tell it UTF-16 or something, and it's more complex. But the simple thing is you just say, I'm going to clean up my data on the way in, I'm going to clean it up by running it through decode, and I'm going to encode stuff on the way out. And so sockets are the place where this comes into play. And so you'll see we'll always do this encode and decode every time we're sending data kind of outside of Python and inside of Python. So now that we've talked a little bit about character sets, we're going to make this even easier so you don't have to use sockets. urllib is a bit of Python code in the library that does all the socket stuff for you. Okay, so now we're going to write a web browser again in Python, but it's going to even be shorter than what we did before. We did it in 10 lines using sockets. Now we're going to do it in 4 lines with urllib. So urllib really is just because the idea of opening a connection, sending a GET request, sending the new line, retrieving the stuff, breaking the headers out, doing all this stuff, that's so common, why not put it in a library to save ourselves some effort? So here's how we do it. We're going to read it in, right? We're going to import this library, so it's not part, we had to import sockets before, but we're going to import urllib now. And so this is really quite simple. It's like elegantly simple. You say urllib, that's a library, that's a part of a library, a module within the library, and this is a function. So let's call URL open, and then give it the URL. Now that's a string which it's going to encode automatically for us. So it's taking care of all kind of pretty things for us. It does the get, it does the encode. Look back at that previous code. That's kind of what urllib is doing for us. Okay. Now what urllib also does is it makes the connection, encodes the GET request, and then it actually retrieves, at this moment, it retrieves all the headers and keeps them for you for later. You can get the headers, but we're not going to see the headers. And it returns to you an object that looks pretty much like a file handle, because you can put this in the for clause after the in. Now it's going to run that loop 1 time for every line of this file. And so the lines we're going to get back are bytes, and so we have to say decode. It doesn't do that for us automatically. We are going to have to decode them, and that's because we might need to decode them with a particular character set here. And then we're going to do our strip, and we're going to just print this out. So that's like open a file, read through it, and print it. This is open a URL, read through, and print it. And that's as simple as it is. And so that's what happens. This is romeo.txt, and it prints out. Now the thing to notice is that there are no headers here. The headers have been sort of consumed in the URL open. Again, there is a way to say, hey, give me my headers, but for now, this is just going to eat the headers and keep them, and then you get to read all the data, and the loop runs, and this loop runs 4 times, and out come the 4 lines. You can go ahead and run this one. It's super easy. I mean, literally super easy. And if you can do anything you want. I mean, treat it like a file. You just have to remember to do the decode bit when you treat it like a file. And so that code import it. We're going to open it. We're going to make a dictionary. We're going to loop through. We're going to split it. We have to add the decode just to make sure, because that line is bytes, not string. And then we're going to go, our words. We're going to go through the line, and then each line we're going to bounce through the words. The inner for loop is bouncing through the words, and then we're going to go to the next line, and then we make ourselves a dictionary, and we print that dictionary out. Now this in effect, other than importing this, opening it differently, and doing the decode, this is exactly how we would process a file. And so by using urllib, you really sort of reduce the complexity of retrieving and reading network resources to the same complexity of reading and dealing with a file locally on your hard drive, which is kind of pretty. So one of the things then we can do is read web pages. That was a text file, but you can get HTML. And so here's how you read a web page. And it's the same kind of code. We open a URL. This one happens to have HTML in it, and we read through it, and out comes the HTML. Remember that the headers are there, but they've been eaten by URL open for us. And now we could write a browser that would parse these less thans and greater thans and make links, etc., etc., etc. So if you can come up with ways to find these links, you could actually write a bit of code that would then have a loop that would go up and open a new one. Pull out the links, open a new one. Pull out the links, open a new one. And so you could make a thing that would you could write a program that would retrieve a page, find the links in the page, and then retrieve those links. And we'll actually do that before the end of the class. And so Python is a very popular language at Google, and I wonder if I think it's a pretty safe bet that the first crawler that they wrote to crawl the web, to build the index, was Python, because literally that's all it takes to read web pages and pull those web pages into your web crawler database. So I don't know, are those the first 4 lines ever written to Google? Who knows? So the next thing that we'll talk about is how you handle that HTML. HTML is kind of yucky and nasty, and so it's not as simple as regular expressions. Regular expressions might help, string parsing and split might help, but it's just too crazy. So we'll talk a little bit about how to use a library to make HTML parsing a lot easier. We are going to be talking about some code. If you want to download all the code, it's right here. It's all single big zip file. And all this sample code, the one I'm going to talk about is urllib1.py. It is not very exciting. It's short. That's what's kind of nice about Python code. And it's really, if we go and take a look at the code we played with just previously, which is socket, the idea here is urllib is something that Python has produced for us to make socket communications and HTTP communications a lot better. So socket, this is making socket calls underneath it, but there's a library that makes this quite simple. And so we have to do some imports. So instead of importing socket, we'll import these URLs. We are going to create a handle, URL request URL open, and just pass in a string. So we're not encoding this, we're not sending get command. All the stuff we did in the previous sockets example is gone. And then we can just put this as a for loop. And so we're not using this lower level read and write code, we're just using a for loop. And so that literally is going to read the text line by line. And the line does come back as an array of bytes, so we have to do a decode, but then we got a string, and then we can do a strip on it. So this is like a super simple, super simple. So there we go. Now the interesting thing is you also don't see the headers. We just read the contents. Now it turns out in urllib, and we'll see this in later more complex application, you can get the headers if you want. You can get various other things. So that's urllib, a simple urllib tool. Now we can also use this in URL words to show you something quite interesting, and that is, if you look at this from right here, other than the decode, this is exactly the code we wrote to compute the words, right? So other than this line.decode, this is just a open something up. In this case, we're going to open a URL. We're going to create a dictionary. We're going to loop through each of the lines in that thing. We're going to decode them and then split them. So once you do line.decode, this is now a legitimate internal Python string. We split it, we run through the words, and run the counts. And so this is exactly like code that we did before to run counts. And so Python 3 URL words. And so that gives us a dictionary, which is the word frequency. And we could do all kinds of crazy stuff in here, you know, with sorting and all the kinds of things. The important thing is once you've done this and this, the code, other than the need to decode these lines when you first get them, it really works just like makes a urllib makes URLs function inside Python very much like files. So these are short and to the point and very simple, and I hope that they were useful to you. So now we're going to talk about what you would do with a web page once you've retrieved it in a Python program. Call this web scraping. And so web scraping or web spidering is the act of retrieving a web page, extracting the links from those web pages, making a queue of unretrieved links, and then moving on. And eventually the idea is if you had enough time, energy, bandwidth, and storage, you could find your way to most of the web pages on the internet that are point to or are pointed to by other web pages. And so you might have all kinds of reasons to scrape data. You might have a blog that you posted. You might have, who knows, maybe you put some data in a system. Maybe the system's being shut down because it's being retired. You can do all kinds of things. You could write a little thing. I was talking to somebody who wrote a thing to retrieve something and check, and then send a text when something changed. All kinds of stuff. Or you might make yourself a search engine. But be careful. Not all websites are happy about you using a robot to retrieve their content. Some of the websites, as we'll see, demand that you log in and they track what you do, and if they think you're doing something bad, they will shut your account off. Other websites will track what you're doing without you logging in, but then shut your address off. And so you have to be careful. You should read up. You should figure out what sites allow you to scrape them. Now I have some sites that I've set up that you can play with to make it so that it's legit. So parsing HTML is difficult. Some of the simple examples, you could probably write a regular expression or, certainly some splitting and some whatever. And what you would find is you would write that code and you'd retrieve your first 5 web pages and it would seem to work, and then it would encounter some really weird but legitimate HTML. Or maybe even sort of slightly broken HTML. So the web is full of broken HTML, and your browsers just look at it and go like, oh wow, more broken HTML. But they don't put up error messages, and so people just leave broken pages up. But your Python program is going to see those broken pages. So what you would do is you'd be like, oh, here's a new weird way to do an anchor tag. I'll change my code. Oh, and then run for another 100 pages and like, oh no, here's a new weird way to do an anchor tag. And the problem is that you're going to find a lot of different ways to mess up an anchor tag. And someone has already done that. There's a software called Beautiful Soup, and we have installation instructions on how to use it. And really what it is it's somebody just spent months figuring out all the nasty things that could happen and compensated for it and gave you a nice wrapped interface that just says, look, you give me the HTML and I'll give you back the tags, okay? And so it's called Beautiful Soup. And so you have to install this. There's a couple of ways that you can install this. If you're good at extending your Python, you can just, extend and install Beautiful Soup for all Python programs. If you can't change your
computer's configuration because you're on a school computer or you're using a USB stick or something, then there's a way to download this file that I've created called bs4.zip. And so what you do is you end up with your file called, URL links.py, and then a little folder called bs4, which is a folder that has a bunch of files in it from this zip file. And then you can run it. And so it'll pull it in, and you'll import from BS4 Beautiful Soup, and that's either going to pull it in from the folder you do, or if you have installed it using the Python installer, it will also you don't have to put this file in. So it's up to you. You can either do it one of two ways. So this is a little bit of code. Now, Beautiful Soup is a complex library, and so just because this looks easy, doing things in Beautiful Soup, you might have to actually read a bit more to figure it out. But we're going to just read this. We're going to import Beautiful Soup. We're going to ask for a URL right here. We're going to take that URL. We're going to open it. URL open. They give the URL and read the whole thing. That means we're not writing a loop. We've read the whole thing. That's okay as long as you know that the file's not so large. And then we're going to pass the data we got back. And this is going to be bytes, but Beautiful Soup knows all about bytes and all about UTF-8, and it figures that out. And you just say, hey, take that stuff I just got and tear it apart using HTML and give me back an object, a soup object. Now the soup object is something that you can run queries against. So it parses it, it deals with all the imperfections and inconsistencies in this HTML byte array. And it fixes that and gives that back. And so there's various things you can do, and you got to go look at the Beautiful Soup documentation. It could be a whole class on Beautiful Soup. So here's a thing you can do is this object, you can sort of call it like a function and say, hey, give me back the anchor tags. And anchor tags, of course, are the tags that say href equals blah, 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 /a. So all of this is an anchor tag. And then we're going to loop through the tags because there could be more than one of those anchor tags in the file. And then we're going to pull out that href. And that's what this does. We're going to loop through all the tags and print out the href. So if you tell it to go to drchuck.com, it will show you the one external link in drchuck.com. And so I've got an assignment that sort of goes into that in some more detail. But this chapter has been a whole bunch of interesting stuff. We started with the TCP/IP model and talked about sockets that are phone calls between computers, and then how applications protocols are developed to say what we say on those phone calls. And we've explored then the HTTP protocol, which is probably the most likely thing you're going to see. And then we played with all this in Python and saw that Python is really good at this. You can write extremely simple and small programs to do some extremely complex and powerful things. And again, that's why people like Python, is because it makes the complex simple.
We're going to do a little bit of sample code. If you're interested in getting the sample code, you can download this zip here at pythonforeverybody.com, materials.php, and you will download and you will get all the files and all the files that I'm looking at here. And so the one I'm going to play with today is the file called urllinks.py. So the first thing you got to do before urllinks.py works is you have got to install Beautiful Soup, and I've got some simple instructions at the beginning of the file. And so one way to do it is install it using Python install process to install this Beautiful Soup for all Python applications. And if you are the owner of your computer and you're going to use Beautiful Soup a lot, it's a fine idea to do that. But I want to show you a simpler way that if you don't own your own computer and you just want to make it so that Beautiful Soup works, you can download this file right here, Beautiful Soup 4.zip, unzip it, and put it in the same folder as here. And so if you look in this folder, I have a subfolder called BS4, and that's the unzipped version of this. And it has these things. I didn't write this code, so I'm sorry if the name is bad, but this is the code to BS4, and this is what's in BS4.zip, and it's in the same folder as urllinks.py. And so what happens is when you do this from BS4 import Beautiful Soup, that either can go to sort of this global magic place that Python installs stuff and pulls in the beautiful soup object, or it can go to the folder BS4 and pull it in, okay? And so that's how that works. So you have to do one of these two things. I prefer to keep it simple, download and unzip this file and put it in the same folder as this code, and away you go. So from the previous example, we're going to use urllib, of course, and then we're going to pull in the beautiful soup. From the beautiful soup 4 library, we're going to get the beautiful soup object. Now, if you do this with SSL, if these websites we're going to play with have SSL, you pretty much have to do this little hack. And these 3 lines, don't worry too much about it. The whole idea, you can do Google on Stack Overflow and figure this out. But this is the way that you ignore errors when you have SSL certificate errors. And so we have to add this parameter context equals CTX, which is this variable that we create. So this part and this part sort of just do them. If you don't, you can take them out actually, but otherwise you won't be able to do HTTPS sites. So let's take a look at what we're doing other than dealing with the HTTPS problem. Going to ask the user for a URL. We are going to retrieve all the HTML. We're going to do a URL open, just like we did before. Now this would return us something we could loop through line by line with a for loop, but instead we're going to say, hey, read the whole thing. And that basically returns us the entire document at that web page in a single big string with new lines at the end of each line. And this is not an Unicode, but it's probably a UTF-8 string. But it turns out Beautiful Soup knows how to deal with UTF-8, and it also knows how to deal with Unicode strings. So what we're saying is, Beautiful Soup, read through and deal with all the nasty bits, right? So HTML is like very, very flexible. So drchuck.com/page1htm. And so if we take a look at the source of this, view page source, make this bigger, you know, you might be able to do regular expressions, but it does things like break stuff across lines. There could be a line break here. There could be all kinds of things, right? And so writing, you know, regular expressions or splits or whatever is really hard for HTML. And so what we do is someone has written this. It's called Beautiful Soup. And it's basically, this is the code, and it's based on a joke from a children's story. It basically, someone has just went through and figured out all the bad things that could possibly happen when you're reading and parsing HTML. So either you use it or you will slowly but surely derive all the things that it doesn't work. And so when we look at this line right here, this line at a high level is saying, we're giving you ugly, nasty HTML that could make no sense whatsoever. Please read it and have all the brains that you have and all the weird stuff, figure that out for us and give us back an object. I happen to call it soup. You don't have to call it soup. An object, and that is a proxy for that HTML. But this soup object is clean. And so what we can do is we can sort of retrieve all the anchor tags. So we can talk to this object and say, ask it, give me the anchor tags. What's an anchor tag? Well, if we take a look at this source, the anchor tag is the A through the /A. That is the tag. It is the tag. It is attributes that are on the tag. It is the text within the tag and everything. And so that's what we're going to get. Now, I called it tags plural, not because plural matters at all, but because we're going to get a list of tags. Because even though this web page has lots and lots of tags, if we look at, say, drchuck.com, and view source, whoa, that's kind of small. View page source, right? And we go look for A anchor tags. We got 45 of them, and they all kind of have weird stuff in them, right? So this line will give us back a list of tags. It will give us all the tags in this document. So it goes, the tag goes from there to there. And then what we're going to do is going to write a loop to loop through all the tags. So that's basically hopping, like it's hopping through the document, sort of like this. That's what it's doing. Hop, 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 hop. And it's pulling out the text of the href attribute. So it's going to pull out this bit right here. Oh, whoops. Oh, darn. That was so cool because that's a flaw. Look at that. This is my own page. There is no closing quote here. but it's going to work because HTML soup is like, oh, I know what to do about that. I can deal with that. So let's check to see if that one works, because that's like a mistake. But that's one of the things we like about Beautiful Soup. So we're going to read through, and then we're going to pull out all the hrefs. So this is probably thousands of lines of code that you really don't want to run. So Python 3 URL links.py. And so let's start with a simple one, http://www.drchuck.com. And it reads it. Oh, that's actually the card one, because we got a whole bunch. Let's see if the Sugi one worked. It found that one. It's right after sakaiproject.org. Where is that? Is there another Sugi? Oh, no, it didn't find that one. That's kind of funky. Look, it found it wrong. But that's okay. So you see it found all these and did a lot of nice stuff for us. If we do it, Python 3 URL links.py and do the easy one, http://www.dr-chuck.com, page 1.htm, we will only see one. And there we go. Now, the SSL is if you are looking at a page that has SSL, Python URL links to, so I'll go to like https://www.si.umich.edu, and that will get a bunch of links. And so you'll see, if it wasn't for that, so all kinds of stuff coming back, and if it wasn't for this bit right here and this bit right here, this HTTPS wouldn't have worked. And it's not that that website had a bad URL. It has a certificate that's not in Python's official list. And so the URL is okay. So that gives you a quick summary of using the Beautiful Soup library in Python along with the urllib.
Hello and welcome to Chapter 13, Web Services. So what we've been doing so far is we've been using the request response cycle. We've learned about sockets, we've learned about urllib, and we've actually learned how to pull HTML and even flat text off the internet. But what we're going to talk about now is using that same request response cycle to retrieve information that is specifically designed for programmatic consumption, so that, you know, we had to have this Beautiful Soup which sort of did a hack job or solve the hard problem of parsing HTML. But why not produce data in a format that makes good sense to a program, because programs want to talk to each other. If you recall, the whole idea of a socket is to have one application process sending data to another application process. And so if we think about this for a moment and we realize that we have all these programs, they could be written in different programming languages and they're all connected. And so they might want to send data back and forth through the network. PHP programs, JavaScript programs, Java programs. And so we have to decide on a protocol that is independent of any programming language. And we call that the wire protocol, because if you were to sort of take some connection and watch the exact characters that go back and forth, that's what you would see if you were monitoring the wire. So that's why we call that the wire protocol. And so the idea is that we have to agree on a format that is going to represent the data, and we can't make it a Python specific format or a Java format. And when we take the data from the internal representation, maybe a Python dictionary, to send it to the wire, we call that act serialization, and that is going from sort of the internal representation to the serial representation or the wire representation. And then here is an example of a person with a name and phone number with using less thans and greater thans. This is an XML example. And then in the far end, in a different programming language, it receives this and then deserializes it and then turns it into some useful structure inside that programming language. And so this is an example of a wire protocol that's using XML, and that's one of the formats we're going to talk about. Another format that we're going to talk about is a format called JSON, JavaScript Object Notation, and it is simpler and easier, but it's not as precise and descriptive as XML is. And so while you'll find that most of the things you run into, especially if you're talking to APIs of one form or another, you'll find that JSON is very common. XML still holds sway in places like documents. So if you look at docx at the end of a Microsoft Word document, docx means that it's an XML version of the representation of a word processing document. So the first thing we'll talk about is XML. So one of the two ways that we mark up data is XML, the other JSON. First we'll talk about XML. We'll talk about XML more for a longer time than we talk about JSON. XML stands for Extensible Markup Language. There was a number of markup languages in the 90s that were out there, ways to send data between computers, and none of them was like amazingly better than the other, but in the early 1990s, as HTML came out, the idea that we could use less thans and greater thans, you know, or angle brackets, some people call them. Once HTML made angle brackets popular as a representation format, it was pretty natural that we would find a data representation format that would take a similar approach. And so inside XML, we're going to talk about tags, we're going to talk about attributes, we're going to talk about data, and we've already talked about serialization and deserialization. Serialization is the act of taking data inside of a computer in one programming language, setting it up for transport, transporting it across, and then taking it back apart and turning it back into the data in whatever internal data it needs to be in the destination system. So here's some basic XML, so we can take a look at the various things that make up the XML. So it's very much like HTML in that we have tags, less than, greater than. The difference is we get to name the tags anything we want rather than the A tag or the P tag or the H1 tag. And there's a beginning tag and an ending tag, and they're bracketed together. And there's syntax errors in XML. Syntax errors in XML are more severe than syntax errors in HTML. It's supposed to be right, and if you send bad XML, it's likely that the far end will not understand it. So we have a beginning tag and ending tag, and so like name and slash name are a beginning and ending pair. Then there is the actual textual content, and that is the material between it. And then here's a phone and slash phone, and we have this thing called the attribute. Key equals value. The key doesn't have double quotes. The value always has double quotes, and this is like href equals on an anchor tag. And sometimes you have what's called a self-closing tag, where you don't actually have a closing tag. You have all the data that you need in the attributes, and so you don't even bother putting an empty text area in a closing tag. So that is a start tag, an end tag, attribute, and then a self-closing tag. Those are some basics of XML. In general, XML doesn't care too much about white space. It does in the text areas, so in here it matters and here it matters, but things like we can indent this a little bit differently, and we tend to indent it in a way to make it look reasonable. Although once you have programs sending it back and forth, they tend to send it more compacted just for efficiency purposes. So one of the concepts is that there is a hierarchical structure within an XML document, and there are parent nodes and child nodes, and you can think of these as simple nodes that is a tag in some data, or a complex element that has a tag that includes other tags, some child tags. And there's a couple of different ways we can take a look at this. The simple and more natural way to think about this is a tree with parent-child relationships. So here we have this A tag on the outside, and that's the top level one. You can only have one outer tag, and you can't have, you know, another tag down here. So you have to have one tag that's sort of the root tag for everything in this XML document, and it has two children. So the C tag and the B tag are two children. So the B tag is a child of A, and then C has a D and an E tag that are children there, and then the textual data we model as a child of each of those tags, and you'll see in a bit why it's best to do that. So that is the way to think about this as a tree, to represent that XML as a tree. If we add attributes to it, and this is where you kind of see why it's nice to take the text area and make that be a child of the node, an attribute is a different. So the text is a special kind of child, and you can literally have more than one attribute. You could have x equals 2, you know, zap equals whatever, and these could have a couple of different attributes. The w attribute is a value of 5, and that's the 5 down there, and so you could have multiple ones. You can only have one text node. Now, in the case of A, you have a whole bunch of text nodes, but these are because there are child nodes. Within one simple node, you can only have one text element. You can also think of XML as paths, And the easiest way is to sort of look down this tree version and look at from the path from the parent. So you go to A, then the child B, and then X. So at position AB, you find X. So AB is the path up to the root. So ACD, that's this one, is the path to Y, and ACE is the path to Z. And so you can think of these as paths. Part of what we're doing is we're coming up with ways to walk through and parse trees of XML data. So the next thing we'll talk about is how we determine if a particular XML document is legal or meets the contracts that two applications have set up.
We're going to do a little bit of code. If you want to get your hands on the code, go to the materials website, materials.php, materials.php, and download the sample code. The code that we're going to work on today is the XML code, and we need to be able to talk XML to work with web services. And so here's one of the examples from the book. It's xml1.py. And so later we'll be pulling XML and JSON from the web, but for now we're just going to put it in a triple quoted string, so data. And we're going to use a built-in XML parser in Python called element tree. And when we say import XML etree element tree as ET, this as ET gives us basically a shortcut handle for it. And so the idea, this is a string, it has less thans and greater thans. It looks like structured information, and it is. But really at this point it's only a string. Now we have to call this ET from string to read this and give us back a tree object. And what it does is this might blow up. This code might blow up right here if there was a mistake in it. Okay, and matter of fact, I can probably put a mistake in. Let's see if I can delete this and save it and run this code, and we'll see that it will blow up. Right? And so it blew up here in line 8. Element tree blew up, it blew up in line 12 of the code, which is right here. This failed because the line 8 of the XML string was wrong. So let's put this, that back in. So now it's properly formed XML. So this tree we get back, I name it tree just because I always name it tree, but you could name it X. So the key is tree.find goes and looks for a tag named find, and tree is no longer got less thans and greater thans in it. It is went and turned these into objects within objects within objects. So tree find name says I would like to find the tag name, and that's what this bit is right here. And then .text is going within that and grabbing that text. Okay. And if we say tree find.email, then that's going to give us this. And then that's that object. And then .get asks for the contents of the hide attribute, which is the string yes. Okay. And so if we run this, now that it's fixed, Python 3 xml1.py, it will pull in and get the name and the attribute. So it pulled the chuck out. And so you get this object and then you kind of dive into that object. And so that's xml1.py. If you've got a tag, you can either get the text out of the tag or you can get an attribute out of the tag. So now let's take a look at xml2.py. Again, we import element tree and we have a tag. And XML's always got to have a single outer tag. But this time we're going to have, in effect, a list. Now let's line this up a little better. There we go. That looks a little prettier. And so users, the fact that it's users doesn't mean anything, but we often come up with semantically meaningful names for these things. Users is going to have as its children a list of user tags. Okay, so the children under user, user under user, and then this has each of these as a tag. So we want to parse this, and this is a common thing we want to do. And so again, the first thing we do is we read the string to just take this. It's a triple quoted string going from here to here. And then we're going to, instead of doing find, which gives us one tag, we're going to do find all the users tag, the user tag that is a child of users. And we get back a Python list of the tags, not of the text, but of the tags. So there's a one tag, and there is another tag. And so we can do len of that, so we can see that we got 2. And then we can write a for loop, and this item is going to iterate through the tags that are the user tags that are children of users. So the first time item is going to be this tag, a tag, remember, and then the second time it's going to be this tag. And so we can do things like find and get, just like we did with in XML1. So running this is not too exciting. Python 3 xml2.py. You see that there are 2 users. That comes from this print right here. There are 2 users in there, and the first one, if we go into name and we go find the text within the name tag within user, then we get Chuck, and then we get the ID, which is 001, so we find the ID within that item, and then we get the text, and then we look and we grab the X attribute off of that, and so we see Chuck 001 and 2, and then in the next tag the for loop continues, and we print that out. Okay, and so that's just a basic run through of the XML from the chapter in the Python book. Okay, thanks.
So now we're going to talk a little bit about XML Schema. XML Schema is a language that allows you to decide on whether or not a particular XML document meets a contract, an arrangement. So you have 2 pieces of software exchanging data using XML, and what if one of them, if they're all working, nobody really worries too much about it. But if all of a sudden one breaks, you change one side and the other one breaks, whose fault was it, right? Was it the side that got changed or the other side? And so you could argue. So what you like to do is, before you set up these arrangements between these applications, set up a contract. In a way, they're kind of like the RFCs are, except that their scope is between pairs of applications. And so it itself is XML, and it basically, what we do is we take an XML document and an XML schema contract, and then we either say that's good or that is bad, and that's called validation. A piece of software that validates XML when given a schema is called a validator. And so an XML document, here we have our little XML document, we're passing it to the validator, and then we have a schema contract, which is itself XML. It's kind of a particular kind of XML, that XS: complex type. That's just a tag. Colon is a legitimate character for the name of a tag. Name equals person, that's just an attribute. And so XML schema is a particular format of XML that renders an opinion about what XML is supposed to look like. So there's a number of different XML schema languages. The one we're going to look at is one that's kind of came a little bit later, that's very common, called XSD, which is the World Wide Web Consortium's schema specification. Often you'll find files that have suffixes of .xsd that actually contain the XML, just like we're going to show you. So if you recall, there are simple elements which have text children, and then there are complex elements where other nodes are children of other nodes. And so we can say this, and so here we have a little bit of XML, and the XML schema that makes sense with that. So what we're saying is the outer tag of this legitimate XML is supposed to be a complex tag with a name of person. And so there we go. That looks good. Good, good. Then there is a sequence, and then there is a simple element, a name of last name, looks good, and it's a string, that looks good. Another tag that's of a named age that's of type integer, that's good. And then a thing that's called date born, and then there it looks like a date. So we check all these things, and we can basically say, yup, that is a good XML document according to this schema. And you don't have to write this generally, but there is software that reads these 2 things and comes back with a true or a false, and might even have some detail as to what went wrong with this particular schema. Here's some more that you can do with a schema. We can do things like, have a complex type, we have a sequence. Here we have a string, full name, and a string child name. But we have this min occurs and max occurs. So min occurs is the minimum number of times it can occur, and maximum is the maximum. So min occurs equals 1, max occurs equals 1 means it's required. And so this is required, and we don't have 2 of them. 2 of them would be an error. One of them is fine, so that's good. Here, the child name is min occurs 0, max occurs 10. So we have 4 here, and so that's good too. And so that is another kind of XML schema constraint that you can have. Here's a few other data types that we can do. We've done the string, we've done the date. The date looks like this. Dates are 4-digit year, 2-digit month, 2-digit day with dashes. Now there's lots of different ways to represent dates, but the nice thing about this, and you have to put the zeros in, so 09 for September. It means that these are sortable as strings, so that if you do all your dates this way, they're sortable as strings. So you could argue what is prettier, but for computers we don't worry about that. We're arguing about what's the most functional. And then the date time is that same date format with zeros, followed by the letter T, and then followed by hours, minutes, seconds, 0 filled, right? So 9 o'clock is 09, and then the time zone, which we'll talk about a second in the next slide. You can have decimal numbers and you can have integer numbers as well. And so we are able to sort of render an opinion as to what is good and what is bad in the resulting XML. So dates are kind of interesting. There's, again, we have lots of different formats of dates, 9, 10, 9/10/2002, right? That's a format of a date, but that's one. There's another format of the date, which is 12 December 2 whatever. And so this is how people show dates. Computers don't want to have all those different dates and don't want to figure those out. They have libraries that produce dates and make them look pretty and for particular locales, but computers really want dates that work best for them. So we just say, okay, we're going to have this year, month, day, time, and then 0 fill, hours, minutes, seconds, HMS, and then time zone. Now, computers even prefer a time zone. I don't know if you've used something like your Google Calendar and you take a flight or take a train trip and you end up in a different time zone, everything switches. And that's because Google Calendar is not really storing the time zone that not storing the dates relative in your current time zone. It's storing them in what we call universal time, or Greenwich Mean Time. Zulu time is another word for that. And Z means this time that is the time in London, England, Greenwich Mean Time. And so the thing is that means if this data moves between time zones or crosses the international date line or standard daylight savings time or anything like that, none of that changes. And so we have this internal date and time that's very common in situations where computers are exchanging data that then gets shown with a time zone, converted to the time zone or the local format. That's the right way to do that. And there's a standard for how dates and times are supposed to look. So here's another little example of some stuff. Let's see what we got. Now, if you see this little question mark XML, that's not a problem. That just is a way of sort of putting a header on the whole document that says it's an XML document, telling it that it's a UTF-8 document. And that's not really a tag. That's sort of like a marker on the file, so that you can put that there, but it doesn't harm the XML. The outer tag is this tag right here, XS::schema. And then what else we got? We got an address. We've got a string. We've seen all those. Here we have country, and we're going to have a restriction that basically says this is a simple string, but we're going to make it so that you have to list one of these 4 as the country code. And so here we are down here, and that's UK, and that's UK, and so that is valid XML. Another couple of examples here. Let's see, string. Max occurs unbounded. That means infinite number. There's no limit on the number. You can do that. Min occurs of 0. Excess positive integer, we've seen integer, but you can also say it's got to be a positive integer. Decimal, we've seen that. And then use equals required is just another statement that you can make. I'm not trying to get you to the point where you can do XML schema, just get you a sense of the kinds of statements that we can speak about when we're talking about what is and is not legitimate XML. So let's talk a little bit about how we might talk XML inside Python. And so, like most things that are in this extended part of Python, we have to import something. And so this is the name of a library, XML eTree element tree. And then as ET, this ends up being a shortcut. So we don't have to type these long things. And so ET is the same as typing that. It's almost like a macro. Now, normally this XML is going to come somewhere from the network, but I'm just going to put this in a string. I'm using a triple quoted string. And so that means that this triple quoted string starts here and ends here. And all these new lines that are here are actually part of the string. So this is kind of like I opened a file and read the whole thing in. But just to keep this totally self-contained, I'm putting it in a string. So the XML would come from some server on the other side of the network. We would get this XML. So that's how it would normally work, okay? So this is the XML right there. And we parse a string of data, and we call ET from string. So we're passing in the less thans, the new lines, the greater thans, all of this stuff we're passing it in. And this could have syntax errors in it. So this might blow up if this had a syntax error, like we forgot the little slash or something, there was a syntax error. But this doesn't have a syntax error. So then what we do is we get back an object. I just happen to call it tree because it kind of is like that tree version of the XML. That is an object that we can then query to pull data out of it. So we say tree.find and look for a tag name name. So that finds the tag name name is this. It's everything. It's the tag and the text. If we want the text, we add .text, and then that .text, that actually refines it to only the word Chuck. And similarly, if we do tree.find email, that tree.find email, that finds the email tag, which is this tag. It has a child attribute, and you can get any of the attributes. You say .get. There's only one text child, but there are many attribute children, and so you have to tell it which one you want. And so this bit right here, all of that will resolve down to that string yes. That's what you're going to get there, yes. And so you kind of build up these little finds and call methods. This is not clearly a full introduction to element tree, but you get the idea that you sort of dive down in with these methods that call methods to get little pieces out and parse all of that. Here is a different example. In this one, again, we're using triple quoted string. We always have a single tag on the outside, and then I have a complex type of users, and in it there are two user objects. So this is kind of like a list, right? So this is more than one of these things. So this user can occur more than one time. And again, we take this, we pass that into from string and get back an object that represents the name stuff. Does not necessarily have to be the same as this outer tag. Just a variable. This could just as be easily as X if I wanted. And so now what I'm going to say is, hey stuff, I want to find the tag, the path, users/user. I want to find all tags that match users/user. So that's going to give me a list of two tags, one tag, two tags in a list. Tag, tag. Oops. So two tags. Now I can print out how many I get. That'll be 2 in this case because I got 2 tags. And then I can actually iterate through the list. All right, so I can iterate through the list. So this item is going to iterate first to this tag, and that tag, now it's like in the previous example, we can look for the name tag within there and pull the text out. So we pull that text out, find the name tag, and then within that find the text. And we can find the ID tag and pull the text of that out. So that pulls out this 001, and I've scribbled too much. And then we can item, which is, this is item, is that whole tag, .get X. So that gets the attribute, that gets the 2. That 2 comes down here. Okay, and then item goes to the next one because item is looping through, so item iterates down to that one and pulls out the name.text, the ID.text, and the attribute .x and pulls all those pieces out. So this is the basic pattern. You saw one where you're tearing into a single thing, and here you're tearing into something that is expected to occur more than one time. And so that's a quick summary of how you talk to XML in Python. Up next, we're going to talk about the other serialization format, JavaScript Object Notation. So now we're going to talk about the other serialization format, JavaScript Object Notation. Chances are good, as you go out there, you will very likely encounter more JSON than you will XML. Not that XML is bad. XML is better for rich and hierarchical documents, whereas JSON is best for just pulling data out of a system and moving it between two systems with the minimum of fuss. This is Douglas Crockford. I have a great interview from him. He's a funny guy, very, very smart. He claims he didn't invent JSON, he discovered it, because it really is based on the literal notation for JavaScript. And it actually looks a lot like the Python literal notation for objects and for lists. Now, Douglas Crockford is quite a sense of humor. He wrote this book called JavaScript, The Good Parts. That's the little one right there. And then JavaScript, The Comprehensive Guide. And the sense of humor is all the stuff that's in JavaScript that's not too useful. And while this is sort of a tongue-in-cheek, it also is trying to say that JavaScript, what Crockford is really saying here is JavaScript is a great language as long as you avoid the tricky bits and sort of keep it very, very simple. And JavaScript is indeed a great language. But JSON comes from JavaScript. You can read about JSON at json.org. JSON is not an international standard. It's not like an RFC. It really is. Douglas Crockford decided to register json.org and typed in some pages, and people started reading it and people started using it. And partly that was because it was truly derived from the JavaScript JavaScript literal syntax. So we're all ready to code. Here is some Python that's going to process some JSON. Keep it straight. Python process JSON. So again, I'm using the triple quoted string here. Now you'll notice the syntax that we are using is not angle brackets, but instead curly braces. And so the curly brace, and then within the curly brace you have key value pairs, name, colon, Chuck, and the key, colon, value. And both sides have quotes. You can also have objects within objects, curly brace, key value pairs, key value, key value. Looks a lot like Python. And then you can do this. And so this is a structure that has one key value pair that's a string, another key value pair that's an object, another key value pair that's an object, and then these are key values within those contained objects. So this is a string that again probably was retrieved across the network from some other place, and we're going to pass that string into the JSON library load s. Load s stands for load from string. So it reads this, parses it, looks at all the white space. White space again doesn't matter too much here unless it's in between double quotes. The white space doesn't matter, and so it parses it and then returns us a dictionary. So the thing that's different about JSON is that its structure and representation are simpler than XML. So in Python, everything either comes back as a dictionary or a list, or a dictionary within a dictionary, or a list within a dictionary, but it's all dictionaries. It's not a separate structure that you have to do gets and finds and find-alls and lookups. So it's right there. So when we get this back, because this is a curly brace, info is a dictionary. And so we can just use the standard syntax of Python. Info subname. Well, that will bring, let's clear this. So info subname will go find Chuck. So if you compare that with the XML, that's just a lot easier. Now, when we have info sub email, that's this thing. So info sub email is that thing. And then sub hide is this. So that's what comes out here. Okay, so it's really nested dictionaries and lists. We haven't seen a list yet, but this is a set of nested dictionaries that it parses. And it's equally simple in other programming languages. This is a little more complex version where the outer element is a square bracket, which means it's going to be a list. And so we have a list of 1, 2 things. So this is a list of 2 dictionaries. So there's 2 dictionaries inside that list. So again, we take this string and we load it into, use the JSON parser to read the string and give us back, in this case, info is a list. It's got 2 items. If we print out info, it'll give us 2. And we're going to iterate through. And so if we're going to iterate through, item is going to first be this, and then it's going to iterate to this. And it's going to print out item sub name, which is going to print out Chuck, item sub ID, which is going to print out 001. Now you'll notice that there is no attributes, and that's because JSON is simpler. But we can have the X, and it just is another item, so we say item sub X, and that's going to print the 2 out. And then it'll iterate to the next one, and it'll print out the same thing for those guys. And so JSON is simpler because you can't represent as complex a data structure, or you have to compromise and map it into a simpler data structure, but then it is lists and dictionaries, and so once you've got it parsed, it is easier to understand and to make use of. So that was quick. So that's partly why everyone likes JSON better, is once you have come up with a format that you're going to send it back and forth, it's easy to make it and it's easy to read it. Now what we're going to talk about is sort of moving up a level. If you've got all these data formats and URLs that you can hit to pull those data formats down, what approach do you do as you start to construct applications that increasingly go from a single application to a networked application?
We're playing with the web services chapter right now, and if you want to get the materials for this course, you can go here and download the sample zip, samplecode.zip. I've got this all sitting already on my computer. I also have the whole thing in GitHub if you want to get it out of GitHub. So the thing we're talking about now is we're talking about the JSON1.py example from the book. And so JSON is kind of like XML, except a lot simpler. And that's why a lot of people like it. It's not that JSON is always better, but JSON is better in a lot of situations that don't require the complexity of XML. So we start to import JSON. JSON is built into Python, but we have to ask to import it. Again, we're using a triple quoted string to put the JSON in there. And JSON looks a lot like Python dictionaries, key value pairs, key value pairs. In this case, this is a key, and the value itself is another dictionary, or in JSON terms, an object, but again, key value pairs within key value pairs within key value pairs. And all these little cursor guys have to, all these little curly brace guys have to line up properly. And so, like all the time, this is a string, which we normally would read and decode from the internet, but for now we're just going to have it in there. Load JSON.loadS says go into the JSON library, pull out load string, and parse this, which turns this set of curly braces, spaces, commas, perhaps syntax errors into a structured object. And if we'd made a syntax error in here, then this would blow up. But if this doesn't make a syntax error, if this doesn't blow up, then we have a structured representation. Now the difference between XML and Python, JSON, is that this turns into a Python dictionary with key value pairs. Okay, and so once we have this, this is a dictionary. And we can say info subname, and that's the exact syntax that we would use to get the dictionary, and that's going to extract this value out of there. And if we want to go in deeper, we can say info sub email, and that's what info sub email is right there, and then sub hide. So that's a dictionary within a dictionary. And so if we run this, Python 3 JSON 1.py, it digs in really fast. And so this is why people tend to like JSON, is because you read the JSON, which is actually a syntax derived from JavaScript, but it looks just like the syntax for Python. So it's moving that's moving an object, a JSON object that turns in directly into a Python dictionary with nested dictionaries. Now we're going to look at JSON 2. And so JSON 2, we're going to see a list, or an array in JSON terms, but it turns into a list in Python terms. So this is a list of dictionaries. In JavaScript, that would be an array of objects, but in Python, it's a list of dictionaries. So we'll just pretend that it's a list of dictionaries. Again, We load the string, parsing, looking for syntax errors. So let's just make a syntax error here and run Python json2.py, and you'll see where it blows up. It blows up at line 15, which is right here. It's like this load s blows up. Now you could put a try except around it to save it, but we're not going to do that. And it even complains. It says, look, we're expecting something here in line 11, and that's line 11 of the JSON, which starts at line 4. And so I'll put my little square brace back in so it's not syntactically broken. So let's run it again and make sure that she runs, and yes, she does. So this parses it and converts from the JSON syntax into a Python, in this case, list, because it's got square braces instead of curly braces. The previous example had square braces. And we can then take a len of it, and it's an array, it's a list, and we see that there are 2 things in there. And then we're going to iterate through, and this item is going to iterate through these dictionaries, that dictionary followed by that dictionary. So the first time it's item sub name, which is this value right here, and then item sub ID, which is this value. So you can dig right into this, but you're not using get, and you're not using the weird extra find or find all or anything. You just are going at these structures directly. And so you can quickly extract this stuff out, and we read through ID is name is Chuck. Oops, name is Chuck. There are no attributes, by the way. X is 2, and so we had to make X. So if you look at the XML, we had this concept of attributes on the outer tag. These things are also not named. We just have to know what we're looking for. So JSON represents simple structures, but it's much simpler to use. So I hope this has been useful to you, and talk to you in a bit about some more JSON.
So the service-oriented approach is a way we approach solving a complex application problem where all the data really isn't present in one computer system. It's somehow spread out over the internet, connected via the internet or internal network. And so the idea is that some applications just can't contain everything. The perfect example is a travel website that can book you a flight, book you a car, buy tickets, book you a hotel, and do all these things. Well, that travel website is neither a hotel nor a rental car company nor an airline. But what it really does is it talks to all these services somewhere else on the web on your behalf, and it makes reservations for you. And so you have this convenient user interface that says, oh, here's your whole vacation. I'm going to figure all this stuff out. Now you say go, and it goes book, 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 and books on all these other systems. Now it requires a lot of infrastructure, a lot of coordination, and a lot of effort to make sure that your application can talk, and these other services that are out there in the internet have good contracts, and you know exactly how to send data to them and get data back from them. And so initially, when you're building a service-oriented architecture, often you have one application and it's all internal. Often it's all one language, and then maybe you'll say, oh, wait a sec, we want to take part of what we do and put it in a second system, and then sort of come up with a set of rules between the systems, and then more and more and more. So now that we're solving our problem using a series of cooperating applications communicating across a network, we're going to talk a little bit more detail about the notion of what we call web services. And in this, we're going to take a different perspective. Instead of building our application and breaking it into pieces, we're going to have an application that's going to really consume an API from somebody else. So there is some other provider of this API that's not us. And so that if you're going to talk to somebody's data like Google or Amazon or Twitter, they're going to say, you have to use our API. So what's that? So an API is a contract that says, look, if you do this, and this, and this, and this, we're going to give you data this way. And they set the rules, they tell you what the URLs are, they'll tell you if it's XML or JSON, and this is called the application program interface. And it's something you read and you understand. And so you go look at the documentation. This is the documentation for the Google Maps API. So it turns out that Google knows a lot about maps. It knows a lot of data. It knows how to search maps. and it actually provides some of those features to you that your application can take advantage of. I took advantage of this at one point by asking all the students in one section of one of my online courses where they were from. And I just let them type in where it was. And then I said, well, I don't know how to code any of that. So I used this API doing what's called geocoding to look all those places up and get precise latitudes and longitudes for the ones Google could figure out. And that saved me a lot of work. Now, these are expensive resources, but I could be patient and make use of these resources, which as long as you use them not too much, they can be free. We'll talk a little bit more about rate limiting and what's free and what's not in a bit. But you start by reading documentation. It says, do this, hit this URL, hit that URL. So if you read that documentation, you will find that there is a URL that you can hit. And they tell you where to go. And then you go to this URL, you add a question mark, and then you say address equals, and then Ann Arbor plus, and there's all these rules. These are called URL encoding rules when you have key values on URLs. The plus means space and %2c means comma. So these are called URL encoded. But don't worry too much about that because we're going to have a magic library like we always do in Python that takes care of this. And so if you were to hit this URL, you type it in the exact right way in your browser, you will get back a JSON document. It's an object that has key value pairs. The first value is this status, then it has these results, and it's a list, and you dive down, and eventually you can kind of find the latitude and longitude of the thing that you are looking for. And so the idea is, can we write a program that can read this? And so here's our little program that reads this. And a lot of this is sort of comfortable. You've already seen some of this. You import urllib. We have to parse them JSON. We grab the URL. And then we're going to write a little while loop that's going to ask for a location. And we can type that location in. And we've got to concatenate with this URL the location equals. And there is a bit of code, a library that called parse URL encode that takes the key and the value, so the address equals, and then whatever this text is that we read in from the user, that goes in here, and it does that URL encoding with the pluses and the %2c and all that stuff is taken care of, and that is our URL that we're going to pass to URL open. So we print out that we're going to retrieve it, prints this out, and if you look at this, it's too long, it has all that fancy stuff on it, and then we read it. We open it with URL open, and then we read it and decode it. So these two things, hit this URL, decode it, and then we retrieved 1669 characters, because it's just in this case, because we've decoded it, data is a string now. That's read is bytes and data is a string. So we read that many characters, 1669 characters, and then we're going to take this data and we're going to parse it with JSON. And we might get bad data here. It might blow up, but it might work. And so in this case, it works. We have an error that basically says if we got a bad thing, we're going to blow up, but in this case, it doesn't blow up. And so now we're going to sort of dig through. And if you go back, let me just go back. So the results, sub-zero, geometry. Let's show you how that works. So results is the first key. So this is a dictionary with a key of results, but then it has a list, and the 0 item, this list starts here and goes there, and I'm only going to show part of it, but there's many things here. So the 0 item is this. This is the sub-zero. And then geometry within that sub-zero item. So if we look at that, it is the outer dictionary, the first item in the list, sub-geometry. So that grabs one part, that grabs this part right here. And then we're going to go into location and lat. And those are just keys within keys, a dictionary within a dictionary. And so you see it says sublocation, sublat. And so that is literally going to pull out of that complex structure, that will pull the latitude out, and then in the next line, pull the longitude out. So we can pull the latitude and longitude out, and then we print it out. We can go into results sub-zero formatted address, and that goes into results 0 formatted address, and that pulls this little bit out. Now it takes a little while to write this stuff, and you have to put a lot of debug, and you don't necessarily figure out this complex bit here at the end, but you know, you print it, you don't get what you want. You say, oh, wait a sec, that was an array, so I got to add a little sub-zero there to get the first one out of the array. But eventually you figure it out. And it's not all that difficult. It's the first few times you do it, I'm like, what am I doing? But after a while you realize, oh, I'm just sort of tearing this apart and digging deeper and deeper into this data structure, which I just retrieved over the internet from Google, and I learned something good from that. So up next, we're going to talk about how sometimes these APIs protect themselves with keys or signatures, and why that happens and how to solve those problems.
We are doing some code samples here. If you want to follow along, you can download the sample code all in a big zip file. I've got it. We are going to be working with the Google Maps API. In the old days, this Maps API was free and did 2,500 requests per day, but now they've made it so that parts of it are behind API keys, and you start having using OAuth and stuff. But they haven't put it all behind this one address service that we've been using. That continues to work. And the basically idea of an API is you go read the documentation, you find a URL, and this is going to Google servers, and you pass in the address. And we have to pass in the address using what's called URL encoding. So spaces are pluses, that's a comma, and then that's a space. And so we have to pass this in a certain way, but if we do it right, we hit this, we're going to get ourselves some JSON back, and that's really cool. And so deep inside here we get the real address, you know, a good address, we get a geometry, you know, we have the location, we got the latitude and longitude, and we can extract stuff out of here. And so we're talking, and this one here is still rate limited to 2,500, but it's one of the few parts of the Google Maps API that is not hidden behind an API key. In a later chapter, we'll show you how to actually talk with the API key in the geodata code. The geoload shows you how to use an API key if you want to jump ahead and take a look at that. But for now, we're just going to take a look at GeoJSON, which is going to retrieve one page and tear it apart. So let's take a look. So we're going to grab the urllib stuff and import JSON. So now we're going to use JSON, but we're going to actually pull the data out of the internet. And so I just take that service URL for Google Maps API. I found that somewhere in the documentation. And then I'm going to have a loop that's going to run forever. I'm going to add the location. And then if I hit enter, that's what this is saying, get out of the loop. And then what I'm going to do is I'm going to concatenate the service URL, which is this, and this urllib parse URL encode gives a dictionary of address equals, and this bit right here gives me the string that leads to putting this address equals, but encoding these spaces the right way. So if you type a space, that bit of code turns it into the plus. So that's important, and I've got the question mark sitting here at the end of that. Then what we're going to do is we're just going to do a URL open to get a handle. We're going to read the whole document, and because it's UTF-8 coming from the outside world and we want it turned into Unicode inside our application, we say .decode. We can ask how many characters we got, and we put our JSON load S. Now up till now we've been just doing load S's from internal strings, but this is now a string that came from the outside world, and we'll put a try except in, and we'll set JS to be none, and that'll be our little trigger. Now we can look for, they give us, if we take a look at the output, they give us this OK, and that status can be a problem and it can complain about things. So we have to check to see if we got a good status. So at this point, if you look at the outer bit of this, the outer bit that we get is a curly brace, so it's a dictionary. Then there is within that dictionary a key results, which is a list. But then the second thing in the outer dictionary is status. And so we can ask if if we got a false, if we got nothing, that we'll quit. If we don't have a status key in that the object or that dictionary, or it's not equal to OK, any number of those things, if this or this or this are all, either of those are true, we're going to quit. Failure to retrieve and print the data out. And when you're starting to read stuff off the net, you often have to put debugging in here like this, like, oh, something quit, I got to figure out, and so debugging it. Next thing we're going to do is called JSON dump-s, which is the opposite of load-s, which takes this array that include dictionary that includes arrays, and we're going to pretty print it with an indent of 4, and then we're going to print that out. And so if you look at my code, we'll see that the first thing we do once we've parsed it is we print it back out so we can see it, and then we're going to dig into it. So let's go ahead and run this code. Python geojson.py. One of these days I will always type Python 3 Ann Arbor, Michigan. Okay, so it ran, and so you see that it retrieved this URL. This URL was constructed and retrieved 1736 characters, and it's JSON pretty printed with an indent of 4, and this is that JSON dump-s all the way down to here. So that's just JSON dump-s, and then it starts extracting. So it's going to pull things out. Now when you write this code, it's really easy to look at this and say, oh great, it's easy. I tend to have to print this stuff out over and over and over as I kind of construct this expression. But if we look at it, the outer dictionary sub-results leads to this array. And if you go look at this array carefully, you find there is only one thing in it. And so that the results is an array. Sub-0 gets us this dictionary. I keep wanting to say object because that's what it's called. And that goes all the way down to here. So that's what we get there. And then within that, we now have an object, and we look for geometry within that object. Where is geometry? Right there. Geometry. Geometry goes from there to there. There's geometry in there. You got to get used to it. That's why it's nice to have this stuff indented. Geometry sub low. Oops, come back. And then we go to location within that. So location within geometry. And then within location we have lat and long. And so this is pulling out this 42 and 83. And then, so we print that out. Take a look. And that prints that out. Pulls that right out of the JSON. These are tricky to write, but after a while you win and you get it right and it's just fine. Okay? And so we do the same thing. Result sub-0 formatted address gets us this. And so that's how we print the location out. And so that's a real quick look at how we would do that with the JSON talking to the Google Maps API. Okay? Hope this helps.
Now we're going to talk about API rate limiting and security. The key thing is that the Google API and the Google data is super valuable. And you could build a website that did nothing but sort of like asked the person for something and then showed them that place and be a map searcher. And you added so little value and Google did all the hard work. And so they protect these somewhat. Sometimes they'll say you can only do 50 of these a day or 500 a day or whatever. That's called rate limiting. And sometimes they say you've got to log in, you've got to create an account and get a key with us and then present your keys. So that means that your account only gets so many. And they keep track of who's using their service and how much they're using it. Google gives you even sort of a dashboard that tells you some of this stuff. It's kind of nice. And so the other thing is sometimes an API is free and then it becomes popular and they decide they're going to put a key on it or a rate limit on it. So you got to kind of play this game with them and the rules kind of change as things progress. So that geocoding API that we're talking about has at one point in time 2,500 requests a day. You can get more requests if you get a key. Now, another API that we can talk about is the Twitter API. Now, Twitter API started out as a free public API, but then Twitter realized that people were making more money off of Twitter's data than Twitter was making off of Twitter's data. And so Twitter makes it so that you have to have an account. You can only request data from their API is if you use your account key to sign that. And so there's a whole series of getting and issuing keys and then using those keys. And I'll just give you a short summary of the kind of code that it takes to build those requests up that have to be signed. So you'll look through the Twitter documentation and it'll say, oh, this URL to get the tweets, etc., etc. and it says do a GET request to this URL and that URL, and maybe substitute a little bit of things here for the screen name you're looking for or how many tweets you want, and they tell you how to carefully construct these URLs. And so here's an example bit of code that talks to the Twitter. Now, for now, I'll ignore the security bit. That's all hidden in this TWURL, so it looks a lot like the last one. We're going to use JSON and urllib, and we have found that this is the API name, blah, 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 list.json, getting a friend list for a particular person. And so that is the base URL that we're going to do, and we're going to ask a person for a Twitter account. If we hit enter, we're going to break out. And TWURL augment, we're going to say, give me the first 5 friends of this particular screen name, the one we just read in from input. And this TWURL, you'll see in a second, it adds a bunch of stuff to prove that you are who you are. It's signing that URL. So you're sending a signed URL, which is nothing more than a whole bunch of crazy characters. We'll see that in a second. We retrieve it, and this is pretty straightforward. We can just, open the URL, read it, and decode it. Decode solves the UTF-8 thing, makes it all so that data is a real string and it's in Unicode internally. Now we can actually get the headers. Remember I told you earlier that URL open bypasses the headers, but it's stored them for later, and we can say, hey, give me back those headers. And that gives us back a dictionary of headers. And the headers, if you go all the way back, are a bunch of key value pairs. Key : value in the headers. And in Twitter, if you read the documentation, there's this x-rate limit remaining that tells you each time it returns to the API, response to the API call that you made, it says, look, you've got 12 left, you've got 11 left, you've got 10. So you can print that out. So this prints out how many you've got left. Then we parse the JSON data. We're going to print it so we can debug it. This dump to string, and then printed. Indent equals 4. This is called pretty printing. And it's indenting things really nicely so that you can make more sense of it. Whereas when these things are when programs are talking to each other, they don't really make the output look particularly pretty. And then if we're going to go through, we have the outer thing of users, and we're going to print out the screen name and go grab the, for each user and users, we're going to print their screen name, we're going to grab their status text and print that out. And so this is what that data looks like. Kind of chopped a bit. So the thing we get is an outer layer, we get users, and then we get a list, and here's the first user. Now if you look at the actual data, it's much larger than this. Here's a second user, and then we have status text, and the screen name, right? And so those are the bits that we're extracting from that. If you look, we are going to grab the screen name, we're going to grab the status text, and away you go. So you can start with this, but you realize that once you're looking at this and you're printing this out with pretty printing, you can sort of work your way in, knowing that it's either a dictionary or a list. If it's a dictionary, you look up the key. If it's a list, you say which position it is, and then you get more dictionaries within dictionaries within dictionaries, and away you go. And so this code actually, when it runs, it prints out the screen name and then that status and the next person. So it's my first 5, in that case, my first 5 friends and their most recent status, the first 5 people. Now, let's talk a little bit about how this security works. And so you have to go to the website. You have to have a Twitter account. You can't talk to Twitter API without a Twitter account. And then you go to this website and then you set up a key. You say, I'm going to build an application that is going to consume the Twitter API. And then you go in, you have to work through, there's documentation on how all this stuff works. You set up an API key, you set the application. So I made a key called Python on my laptop. And it gives us some values. It gives us a consumer key, a consumer secret, a token key, and a token secret. And you get to regenerate these. And there's this file called hidden.py, and you edit them and copy and paste all the stuff from those pages, those 4 values, into these strings. Now, if you download my code, I don't have my keys in there. I got some placeholders for this stuff. So you got to get to this web page that's on Twitter, copy these things in, and then the TWURL code will start to work. It uses a technology called OAuth, which is a way to sign a URL in a way that proves that you have the key and the secret and the tokens, but and it can't be modified in the middle. So once you send this URL, they can check the key and the secret to make sure that you truly signed it without actually sending the key and the secret. It's actually kind of cool and fascinating, but we won't go into it in great detail here. And so if you look at the code in twurl.py, this is the code that does it. It actually pulls in an OAuth library. That hidden.py, that is that code that you've got. And it's got the consumer key, the consumer secrets. This is pulling that from hidden.py. This is a lot of stuff that's using this OAuth library. Don't worry too much about that. Eventually it produces a URL that looks like this. And what happens is this was the base URL you were told to use. Then you have count equals 2 and screen name equals Dr. Chuck. Those parts are your parameters to that web service call. And then all this OAuth stuff is produced by this OAuth code and the consumer key and the secret. What happens is the key gets sent, and the secret does not get sent, but they send this signature, which is based on the secret. And then what it does is it rechecks the signature on the far end. Signature is a long string. By regenerating the signature, because the secret's available to both you to generate the signature and to them to check the signature. So it's kind of like a hash, etc., etc. You don't have to worry about all this. These URLs get really long, and your values that you need are in, the name of the URL is in, and you call this routine. It's called augment. That takes a URL and then parameters and then augments it by adding all this OAuth stuff. And so that's why it's called augment, to augment the URL. And once you got this set up and hidden working, then you sort of just augment the URL and then hit it. Now, if you don't have the right keys or secrets, or you don't have an account on Twitter, then it's going to blow up. But if you get it set up, you will be able to talk to the Twitter API with this. So this whole web services section, we've done quite a bit of stuff, right? We looked at how instead of reading HTML or flat text, we are creating structured data according to contracts, whether it be XML or JSON. We can retrieve and parse that information in a deterministic way. We talked about schemas that define the contracts so that you know if the data you're getting is wrong, you can know who to blame because the schema gets violated.